Welcome everyone to OARC 35. This is our second online workshop of this year. My name is Keith Mitchell. Before proceeding start, I just want to run through a couple of quick presentations. The first is just to give you a little bit of guidance on how we're running the meeting, and the second is for those of you who are new to OARC to give you a bit of an introduction to that. So, information about the meeting. This is an online event. So we have a code of conduct policy for events that applies online as well as at physical events. When you registered for this event, and if you signed up as an OARC member, then you agreed to be bound by these terms. We just want to make sure that everybody has a good experience, and please let us know if you're not having that. The workshop is being recorded. As usual, all the talks will be available on the OARC YouTube channel 2 weeks after the event, roughly. Because it's a webinar format for Zoom, non-speakers are muted during the event by default. This is an interesting time zone challenge for some of us and some of you. All event times in case of DAR are in UTC. There's a couple of social media hashtags that we're using. You will see activity on all the usual social media platforms. We're once again using the Mattermost chat as a back channel for discussion during the workshop. If you haven't already signed up for that, you can sign up at the URL there. We're using the workshop channel in the community team as the default place. So please go to that for discussion during the workshop, or if you want to give feedback about anything that's not working. We will not be monitoring that for comments, for questions to the speakers. You can use a browser for Mattermost, or there are clients. It's cross-platform for just about any client platform that you want to use. For questions, we're sticking with the Zoom Q&A mechanism. So at the end of each speaker, depending on how long the slot is, there will be a 5 or 10 minute slot for Q&A. If you want to speak your question, then use the Zoom raise hand facility under reactions on your Zoom panel. And then wait for the session chair to unmute you, and they will prompt you to speak. If you prefer to type your question, use the Q&A panel in the Zoom interface, and it will be read out in turn by the session chair. Obviously, questions are first come, first served, time permitting. If we run out of time for questions, then our spatial chat room is a great place to catch the speakers during the break, or you may be able to catch them on Mattermost to ask the question. Please identify yourself and your affiliation when asking the question for the benefit of the video and for the benefit of everybody else who's participating. It worked quite well last time, so this time we're going to use Zoom polls for rating talks. This poll will come up during the Q&A at the end of each talk. This is your only chance to give feedback on a specific talk, but it should be quickly and straightforward. If you can just give us a thumbs up or thumbs down, that really helps the program committee. They crunch all the data and compare it to their own ratings of the talks and make sure that you're getting what the audience want. There's also a survey for general feedback on the event, and not just this event, but we're also looking for information on how you feel we might be able to run events later in the year. So please go to that survey if you have other feedback. It's extremely welcome. So we're trying something different for the social. Instead of the social during the breaks being yet another Zoom grid, we've found a new platform called Spatial Chat. Some of you may be familiar with it from Write meetings. It's a little bit like GatherTown that some of you may have tried, but it's a place to hang out during the breaks. You get a little avatar that looks like that picture of me there, and you can move it around the space and you can see and hear the people that you're close to. You just need a web browser for that. There's the URL. There's a password. The password will have been emailed to you, or you will see it on the rolling slides between presentations. You'll also see that there's a little yellow badge there. That designates the OARC staff members who are admins and can help out or address any issues that you're having with spatial. Finally, tomorrow's proceedings restart at 1 AM UTC. On Friday, you reuse the same workshop link as Thursday for this. So that is the meeting logistics. I'm just going to switch over to a little bit about the background of OARC for those of you who haven't been to an OARC workshop before, for those of you who have maybe not been to one for a while, just to say a little bit about where OARC is and what we're doing. What is OARC's mission? We're here to make the DNS work better. We do this through a bunch of different ways. We focus on operational coordination, liaison between operation and research, data gathering, doing useful open source software tools, and basically facilitating an environment where we can share information responsibly and engage in knowledge transfer, and hopefully increase the public awareness of the importance of the DNS. Who are our members? We have around 100 members. You can see that there's some very big names there. They include many of the ccTLD registries in the world, many of the most important GTLD registries, internet number registries, internet service providers, vendors of DNS software and hardware, open source and closed, social media companies, and it's a very diverse community. It's a very supportive community, and you know, we very much value the support that we have from our members. Things that we've achieved recently, the last workshop that we had 180 attendees, which is one of our biggest ever. We just completed our annual day in the life of the internet data collection exercise. More about that tomorrow. Two of the important tools that we have, DNSPerf and DNSCap. We've done some major enhancements and new releases to these. We recently did some important software upgrades to our analysis servers, and also the maintenance automation that facilitated that will be brought to use in other parts of our infrastructure. Our Check My DNS tester has had RPKI origin validation added to it. And despite 2020 being a challenging year, we managed to finish it in a strong year-end financial position. You know, we've had a managed operational continuity and successful online events throughout the entire year of the pandemic. So we're in good shape. What are our technical resources? I mentioned the annual data collection that we do. That goes back over 15 years. So we have a unique 250 terabyte data set. Most of our infrastructure is in Fremont, California. We've been working on a major update to our data store for some time now, which we hope we can finish in the next couple of months. We have a range of open source DNS tool software. I mentioned Check My DNS. There are other testers that go with that as well. And our infrastructure is supported by secondary sites in Ottawa and Stockholm. How do you become involved? You can become a member. We have a range of membership categories for different size organizations. The higher the category, the more contacts you get to participate and use various OARC resources. We have a couple of entry-level categories. Supporters, we expect to make some kind of in-kind contribution. And for small organizations only, there's the blue category. What kind of an organization are we? Our governance works on the basis of an independent legal entity, a diverse base of members. We're financially self-supporting, and I've essentially managed fiscal break-even for some years now. Our budget at the moment is just under $1 million. We're a neutral organization with self-governance through an elected board, which reflects member interest. We have a number of contracted executive staff like myself. But a lot of what we do is supported by volunteer efforts, in particular our program and other committees. And in the US, we have formal nonprofit tax status via 501c3. This is our board. Most of them will be attending some of today's workshop and tomorrow's workshop. These are the staff who are all around. So please do contact us via the various channels if there's anything that you need help with. And this is our program committee. You will be seeing and hearing for most of them through the course of the workshop, and they've worked hard to put the content together for this workshop. We also at workshops usually take the chance to give special recognition to some of our volunteers who have gone the extra mile. This time around, there's two people we'd like to recognize. I understand that Shumon is in the audience today. So hi, Shumon, if you're there. Shumon spent 3 years on the OARC program committee and finished up as a chair. between 2017 and 2020. At this point, we would normally bring Shumon up to the podium and hand him a nice award, and he would get a chance to say something. Since they don't have that chance, he sent us a very kind and generous quote. Here is Shumon, and the award that we sent him this time round. Unfortunately, we weren't able to present it, but hopefully we'll get back to that. So thank you, Shumon. Briefly, next workshops. At the start of the year, we decided that we weren't going to do any physical workshops for the first 9 months of the year. We're sticking with that plan. Probably we will have a short online event in August. And in the Q4, we are hoping that we will be able to do events with at least some physical basis, hybrid events where there's a physical and online participation. We may do the AGM as a standalone event in October for the members. We hope to do OARC 36 co-located with some other event during November. And we're reasonably confident at this point in time that we'll be able to go back to a physical meeting in Austin, Texas in February of next year. So finally, if that's got you interested and you're not an OARC member already, why should you become? Because we have become a member because we have a unique community. With various tools and services that we have, there's a chance for you to influence these, make them useful to your business. We have our unique data set. You're able to share and analyze that. And when things come up, operational incidents, security threats, vulnerabilities, there are various platforms that we have that you can coordinate with your peers. And we're a neutral organization. We're not for profit, and we're free of vested interest in the DNS space. So the final slide that I have is not something that I'm going to speak to, but it's good things that our members have said about us over the years. So that is all I have to say for now. At this point, I will now hand over to the session chair and Q&A monitor for the next session, for Pallavi Aras from the program committee, and also from the program committee, Manu Brutel will be doing timekeeping.
Thank you, Keith, for giving us information about OARC. Welcome everyone to the first session of OARC 35. I'm Pallavi Aras. I'm a member of OARC Program Committee. I'll be the session chair, and Manu Brutel will be the timekeeper for the session. Now I would like to welcome Mark Allman to talk about crucial need for detailed metadata. On to you, Mark.
Great, thanks. Yep, so I am Mark Allman from ICSI. I'm going to talk a little bit from the research perspective about the day in the life packet traces that lots of you make available to us, and ask you for just a little bit more help in making those a little more useful. So before I start asking for more stuff from you, I want to make sure I say that this is really a fantastic resource, the packet traces that everybody makes available through OARC. It's a great research resource, and so this talk is not a complaint. Please don't think I'm coming and complaining. I'm asking for a little bit more help to make this resource sort of a little bit better, but it's great, and I don't want this to come off as a complaint at all. So I wanted to say that sort of first thing here. So when we record packet traces, when we take packet traces, what we're trying to do is we're trying to record a highly accurate version of reality that happens on the network that we're watching for whatever period we're watching. And all packet traces are sort of imperfect in some way or another. We strive to be sort of highly representative of reality, but we do fall short from that, and we fall short for a couple of reasons. First of all, just the technology of recording packets is sort of tough in some environments, and so that kind of gets us away from reality a little bit. And then sometimes we also sort of change things in the packet traces that also doesn't reflect exact reality. And so we can use metadata to sort of fill in the gaps between the packet traces on one hand and reality on the other hand. And that helps us when we're analyzing a data set. So I'm going to go through a few different aspects of metadata that I think would be great if the data contributors could help us out with a little bit. There are lots of other aspects of metadata that one can think about. I'm going to go through the ones that have sort of bit me the most as I look at the day in the life packet traces, and ask for a little help with those in particular. Okay, so the first one is it would be great if we could identify missing data when you send us a packet trace. So this is my sort of quick example of this. So I have a picture here, and I'm using this picture as an analogy of the DITL packet trace that I look at. And so we can certainly extract value out of these traces, like we can extract value out of this picture. Okay, we can see this picture is of a soccer game. We know that the players are wearing cleats, they're wearing shin guards, there's a goal behind it. So we can tell it's a soccer game, football game for most of you probably, right? But there's also clearly missing information here, right? So the player in the white uniform is clearly shying away from something. We have no idea what. We can make some educated guesses by knowing that this is a soccer game, but there's some missing information here, right? This is sort of reality. The rest of the picture is that the player on the white team is shying away from the goalkeeper who's gonna, elbow her in the head trying to get the ball, right? And so this is just sort of, a quick analogy for missing data. It would be nice to know about missing data in packet traces. That don't keep random pictures of high school soccer around, by the way. That my daughter's the goalkeeper in that picture. All right, so there's lots of different reasons why there might be missing data in a packet trace. Some of them are sort of fundamental to how the packet trace was taken. We captured incoming packets, but not outgoing packets. We did sampling, so we only got 1 in 10 packets. Those kinds of things are set up. They're fundamental to how the packet trace was taken. There are other things like, hey, our network monitor just couldn't keep up with the load at some points, okay? And so maybe TCP dump reports, 20,000 packets were dropped during this packet tracing. And that's clearly wrong. TCP dump really doesn't know how many packets it didn't see. But that notion is better than nothing. So if you were to say record that and give that to us, we would have some idea of how close this packet trace is to reality. Okay. Second example is we do transformations to traces. And since I was showing pictures of Leah, I have one more here. Last Halloween, Leah and her friends, Leah's 16, Leah and her friends thought it would be just great fun if they all dressed up like their fathers. So that's Leah as me. And there's some similarities there, right? It doesn't look exactly like me, but there's some similarities. I wear jeans and ball caps sometimes. I have 2 arms, no glasses, whatever. It's not quite the same as me, all right? And so it is for packet traces sometimes, right? And the big thing about packet traces that we often change is IP addresses. We often obscure IP addresses, anonymize them for privacy reasons. And it's really very difficult to look at the DITL collection and know that, oh, JRoot anonymized and FRoot didn't or something. You just can't figure that out. It would be great if folks could sort of illuminate that for us. And not just, hey, the packet traces are anonymized, but it would be great to tell us how they're anonymized, right? We used, prefix preserving anonymization, or we just, completely randomize things. And it would be great to know if the mapping you used in one trace file is the same as the mapping you used in some other trace file, or if they're completely different trace file to trace file. That just adds some information that we can use when we're analyzing. Can we compare across trace files or not? Some more things more bits of metadata that we'd like. We'd like to know where the packet traces were taken. Sometimes we get hints by directory names with, airport codes in them or something, but if you could make this explicit, that would be great. Sometimes it's handy to know, oh, look, this is just Europe that we're looking at, or this is just Asia. If there are any sort of obvious puzzles in the data, we'd love to know about that too. Okay, so
Mark,
if there was some—
Mark, excuse me to intervene. There's about 2 minutes before the Q&A.
Yep. So if there was a routing issue during the middle of the trace and that depressed packets, but that was a real thing, okay, you could tell us that. Anything that we can't get directly out of the trace file itself would be great to know, okay? So if one IP address ends up representing, sort of 10 servers behind a load balancer, that'd be great to know. Other things, if you could see fit to add a little contact information, we always have questions. I know this is a bit of a double-edged sword. I've provided data, and I know you're going to get dumb questions if you put your email address in metadata, like, what do I do with a PCAP? Something like that. But it's really quite handy if you can add some contact information. So how am I looking for you to provide this information? I don't care. That's my answer. First order is just provide it, whether you want to put it in a text file or a Word doc. It doesn't really matter to me. I'm not here asking for, some fancy pants XML schema or anything. Just get us the information sort of any way you can. And if you wanted to go back and do it for the 250 terabytes of data that Keith just mentioned, that would be great too. We do go back to that stuff, and we have these questions. So last slide here, what could OARC do about this? It would be great if the process for submitting data sets also included some way to submit something that wasn't a PCAP, a doc file, a text file, something that had meta information in it. And maybe sort of as a community, we could develop a sort of a template, that data collectors could fill out. What's missing, what's transformed, give me an email address, those kinds of things. And that is all I had.
Thank you, Mark. That was very useful information for researchers. At this time, I would like to remind everybody to fill the poll that would pop onto your screen. This would be your only chance to rate this talk. And we have our first question from Joe Abley. His question is, without metadata in place already, we don't really know who is authorized to speak for data sets that have already been collected. If we are going to start collecting metadata, which I think would be great, perhaps that kind of provenance information would be useful to include.
Yeah, okay. I mean, that's fair. I mean, who can give us the metadata from 2008, right? I don't know. Maybe that's a problem. How about first order? We collect metadata going forward. Collecting metadata going backwards would be great too. Don't get me wrong, and I'm willing to bet that some of these, some of the root operators, they don't change too much. So we could probably get some of that, I would think, but maybe it's too difficult, and I don't know. Maybe that's too big of an ask.
I don't see any hands raised or a question in the Q&A. If anybody has any questions.
Loves metadata. What's not to love?
Okay, I see a raised hand. Eric, please go ahead and unmute yourself and ask the question.
Yeah, in preparing for the last conference, I went through some of the DITL data, and I noticed that I and others were kind of looking for the same things, which is somewhat normalized, which is just what query name, query type, and maybe the source IP of the courier, I think were the three set pieces of data that were being extracted from all these PCAPs. And maybe it would be nice to actually have a subset of all of this data, if those are the parts that most people are interested for the research. Just a thought.
So I don't think that's necessarily a metadata question. That's a data question. And I'm with you, man. Those are the things that I care about. That's the stuff that I extract from this most often too. And I think you're right. I think your observation is right on. And if we could, dig that, a simple summary of every query out like that we could all crunch, that would be great.
Eric, is your question answered?
Yeah.
Okay. I think we have time for one more question. I see Joe has raised his hand. Joe, you're allowed to talk.
Thanks, Ez. Yeah, sorry for not realizing how Zoom worked before. I think this is great. I think we have a severe lack of metadata. Matt mentioned that some of the data sets, some of the uploads do have README files which are there. Maybe if we're going to start with any sort of structured method of storing metadata, I mean, I think jumping ahead to structured metadata itself is probably a fool's errand at this stage, but being able to just identify which data sets have metadata at all would be an advantage. And particularly if you're crawling across a large number of PCAPs across a series of nested directories, being able to exclude stuff that doesn't have metadata and just considering certain sets would be useful. So maybe that's a starting point.
Yeah, anything that makes it easier would be great. Good idea.
Thank you, Joe. I think at this point, we have only one more observation from Sebastian. He's saying, not a question. To note, Kaida tried to manage this issue by implementing DATCAT to carry the catalog metadata and dataset together. But this was not a question. So at this point, I think we are done with the Q&A session for this talk. Thank you, Mark, for answering the question and the nice presentation. At this point, I would like to welcome Matt Pounsett to talk about a better do not probe list. On to you, Matt.
Thanks, Pallavi. Hey, everyone. So I'm going to be taking off my OARC staff hat and putting on an OARC community member hat to talk about OARC's do not probe list. So I've discovered since planning this talk that the fact that a do not probe list even exists is news to a bunch of people. So so maybe this has been good for a couple of extra reasons. So what is this about? So OARC maintains a do not probe list, which is dates back to about 2008. It's was initially just a simple SQL database that was put together by Dwayne Wessels and a couple of other researchers who were doing active DNS probes at the time for research reasons. So querying people's name servers, searching for open recursives, that kind of thing. And they were all, each of the researchers were sort of having to maintain their own lists of people who complained to their, in most cases, university abuse departments about these probes. So the list was put together essentially to help each of these researchers collectively so they could pool their resources on keeping track of those complaints. So it's basically just a list of networks that researchers should not probe when trying to do active measurements. It's populated with bogons, known dark networks like US military networks that were not previously routed. And then any sort of regular networks where an operator had complained about some point about some sort of active probes. So it works pretty simply. I mean, it started out just as sort of friends and family operations. I think only 3 or 4 researchers who had access to it. It was all done by giving those researchers direct access to a simple SQL database where they could list a network and some basic commenting information about why the network was being listed and keeping track of who added the listing. And Later on, the direct SQL access was removed just because it sort of wasn't a great security thing to have OARC's SQL database open to the world like that. And reads of the database were replaced with a simple CGI that dumps out the current list, and writes were moved to being sort of a handwritten admin function, essentially. So why am I talking about a new one? OARC for a few years now has been trying to look for a new home for the do not probe list, basically for the reason that it's sort of off mission. It is not, although it was originally designed for DNS researchers, there's nothing really DNS specific about it. And it has become one of those things that is sort of a significantly manual tool. It really can't scale the way it's currently designed. It works great, and it's a small amount of work to maintain presently, but mostly only because it only sees, you know, an update every couple of years, and there are only, you know, about a half a dozen people who access it. But all additions require a researcher to email OARC. Then an OARC admin has to handwrite some SQL to add that to the list. The submissions don't ever expire. So if a network changes hands, or if a network's policies about being probed changes, there's no way sort of to discover that or capture it. Reading to the list is restricted. So this requires an admin to set up HTTP basic auth for any new researchers who want to read the list. And the published list is unstructured, which in itself isn't a major problem. But there is no information there about why a particular network is on the list. So if a researcher has any questions about reasons why a network might be listed, they'd really need to come to admin to ask for it. And this is essentially what gets published right now by the Don't Probe CGI. Just a bare list of CIDR networks. So OARC, as I mentioned, OARC has been looking for an organization to try and take over the Do Not Probe list for a while. There have been a couple of informal discussions with different community organizations who seemed like they might be interested, but nothing's ever really panned out. So after the last one of these sort of didn't go anywhere, I spoke to Keith about maybe taking this over myself as a sort of a community project to try and put together something that can scale a bit better, that we can you know, advertise among researchers both in the DNS space and in other areas of networking, and try to, you know, help people out by pooling resources on this sort of thing. So the things I'd kind of like to see out of it are an open sign up for logins to read the list. So doing some basic verification on email addresses and approval in explicit terms of service when so that people can access the list, but otherwise not really restricting who can see what's listed. I think it would be helpful to publish the list in some sort of structured format, JSON, YAML, XML, something, just so that people can use sort of standard tools to read it in. That would allow us to also include information about the listing. You know, any comments associated with the listing. If the listing has a particular type, whether it's, you know, from an abuse complaint, or it's in the bogons list or something like that, so that researchers, if they want to, can sort of select which addresses they want to pay attention to. And I'd like to see a way for network operators to list their own networks. I'm thinking about doing something like having somebody who's registered with the application able to list networks, and using something like, you know, tokens emailed to who is contacts for the network address, in order to sort of validate the operator's ability to speak for that network. And then I'm also thinking about the possibility of expiring entries after a number of years, essentially, if they don't get refreshed, with some sort of active notification to whoever registered it in the first place to say, this network you listed is coming up for expiry. If you'd like to keep it in the list, please follow this link, that kind of thing. There are also maybe some longer term improvements, open source API libraries and some common research languages to make it a little bit easier for researchers to access this so they don't have to write their own API client. Maybe some internationalization or localization in the ability, in the part of the application where you actually add listings or visit the website, and do some, publicity basically among network researchers, so that they're aware this exists, and if they do get abuse complaints, they can point people towards it. And along with that, some best practices documentation for researchers. I recall probably about the time the Do Not Probe list was created, actually, an OARC presentation from somebody talking about best practices for doing active probing research, and how to get network operators to recognize that it is research that's being done and who's doing it, and how to report problems and that sort of thing. So collecting some of that kind of information and including it somewhere that researchers can make use of it would also probably be helpful. And open to other suggestions from people about things that could be included in this. Do people have any questions about this? Suggestions? Any of these ideas terrible and I shouldn't proceed with them? What do people think about it?
Thank you, Matt. I think we got one feedback from Paul Hoffman. And I think it's a comment from Paul Hoffman. He's saying, comment on Do Not Probe list. Maybe this can be managed by a research institution that is doing regular probing long term.
Yeah, it could be. I picked it up basically because OARC had been unable to find somebody else to do that. If you know somebody, sure.
Thanks, Matt. Now we have a question from Joe Abley. Joe, please go ahead and unmute yourself.
Thanks. Yeah, hi, Matt. I'm just relaying something from Mattermost, really, but the public suffix list has a similar sort of problem set. They need to authenticate people. They need to find out who's responsible for things. They want to involve a collection of volunteers. They do it with GitHub and pull requests, and they have some workflow wrapped around it. So, unless you particularly want to do this all on your own, I would recommend looking at that and seeing how they've structured it, because it might be quite applicable.
Yeah. Okay.
Thanks, Joe. We have Paul. Please unmute yourself.
Yep. Hi, this is Paul Hoffman from ICANN. This is not related to what I had put in the chat, just what Joe just said. Joe, I love you dearly, and no, you obviously haven't been following what's been going on with the public suffix list over the last few years. It's a complete mess, and I don't blame the PSL folks. It's a volunteer organization. It has all the problems of the tragedy of the commons and such like that. In fact, just today, Ryan Sleevey from Google, who's one of the major volunteers and quasi-leaders of it, posted something on Twitter that basically says, man, it's really too bad we didn't keep this to ourselves. People keep misusing this. So I don't think that is even a vaguely sustainable model. For those of you who are interested in more about the public suffix list, ICANN published a paper on it last year. Come and ask me about it. I didn't write it. We actually had a public suffix list volunteer doing the writing of it, but not a good model for something like this. Thanks.
Thanks, Paul. We have Jeff Houston. Jeff, please unmute yourself.
Sure. Thanks for that, Matt. It strikes me as a little bit weird that you're doing such a, I don't know, hand-driven validation, why wouldn't you just use RPKI signed requests to go onto the block list? You can automatically validate it. They have a time period of validity. Anyone can remove themselves from the list by simply invalidating that particular attestation that they lodged with you. And so it's almost like a variant of a routing origination attestation, except devise your own format, even JSON, and sign it. Work's going on in somewhere in the IETF to do arbitrary signatures of any data structure, and this seems like a very appropriate form of using this. Only the owner can sign it. Why don't you go there?
Yeah, okay. I thought about RPKI at one point. Yeah, I guess it hadn't occurred to me that you could use the same certificates to sign things that sort of aren't part of the original sort of origin validation design. But yeah, I don't. But you're right. I don't see any reason why you couldn't do that. I guess off the top of my head, it seems to me that the uptake of that is still a little low, although I might be behind in my awareness of that. And it might, certainly on my end, it would require a bit more work in terms of dealing with the crypto and stuff like that. But it's not a bad idea. That's definitely something I should look at. Thank you.
Thanks.
Thanks, Jeff. I think we are just about time. I don't see any more questions. So thank you, Matt, for that presentation and answering the questions. Now we will take a 15-minute coffee break and restart at 2 o'clock UTC sharp. So it's a 15-minute coffee break. I would like to remind the participants that the breakout rooms for face-to-face chat will be open, will be running during the break in special chat. And also a reminder to please do not share the special chat link with anyone else. At this time, I would also like to thank the workshop sponsors, Farsight and VeriSign. So we can start the break now. Welcome back, everybody, from the break. I hope you had a good coffee break. Now, I would like to welcome Audrey Randall to talk about Trufflehunter, a tool for cache snooping rare domains in large public resolvers. On to you, Audrey.
So my name is Audrey. I am a third-year PhD student at UC San Diego, and I'm talking to you today about our paper that was published at the most recent Internet Measurement Conference, which was called Trufflehunter, Cache Snooping Rare Domains at Large Public DNS Resolvers. So our group at UCSD mostly measures harmful internet behavior of all sorts of different types. In the past, we've done botnets and all sorts of malware and spam emails. And the thing that most of those types of harm have in common is that they are common. I think I recall that back in 2011, spam was something like 94% of all emails on the internet. So it was easy to find. And the thing about that is, things that are easy to find and easy to measure, they're going to be well studied. But there's all sorts of other types of harm that are much more difficult to study and are therefore not studied as often, including things like hack for hire services and stalkerware and some types of typo squatting. So that's what we're really interested in doing. And in particular, I wanted to have a look at stalkerware, which is kind of an emerging threat that we're starting to see a lot more of, which was particularly difficult to study. So we started off with the observation that, all of these types of harm have something in common, which is that they have to make DNS requests to the servers they require to function. So there is this measurement technique we could use to try and figure out how prevalent they are. It's called DNS cache snooping. I'm sure everybody here is familiar with it. Cache snooping, of course, has a couple of disadvantages. The first is privacy, which I'll say more about in a second. But the second is that as a measurement technique, it's always going to provide lower bound estimates of something's prevalence. But the thing is, if you're looking at rare phenomena, then you're not looking at the kind of things where you're going to see multiple users hitting a cache one after the other. If you're only going to see one user hitting a cache at a time, then cache snooping actually gives you a very good estimate of how much of it is out there. And then in terms of privacy, well, we thought we had a solution for that too, which is that most of the time in the past, people had been doing cache snooping by just scanning the entire internet and making a DNS request to every machine that would answer one. The problem was most of the machines that were answering were actually people's misconfigured home routers. So of course, that's a privacy threat because they have so few users behind them. If you can tell that a domain is in the cache of one of those home routers, it's not too much of a stretch to figure out which user put it there. Public resolvers, on the other hand, like the 4 that we studied, which were Google DNS, Quad9, OpenDNS, and Cloudflare, they let us use cache snooping as a privacy-preserving measurement technique rather than an attack, because they've just got too many users to de-anonymize. But unfortunately, public resolvers are also going to be a lot more challenging to snoop because cache snooping relies on knowing how many caches have been filled, and public resolvers have very complicated caching strategies. They also have some unexpected behavior and occasional bugs because when you're running something that large, it's almost impossible to keep it working perfectly all the time. So from an outsider's perspective, the challenge that we had was this. If a user is going to make a request to a public resolver, first, you have to figure out which POP they're hitting because IP Anycast is going to take them to possibly the closest one and possibly not. Then, once you've gotten to that POP, you're going to have to deal with a whole bunch of different front-end caches. And if a request misses in the front-end cache, it's going to be sent to one of a number of back-end resolvers. And each of those back-end resolvers also have their own caches. So each one of these caches represented an opportunity for us to observe a new user, but in order to count how many caches were being filled, we had to know which ones our queries were hitting. So for the remainder of this talk, I'm first going to describe how we reverse engineered the public resolver's caching strategies, because we needed to know that before we could measure anything on them. Then I'm going to talk about the tool we designed to do the cache snooping, which we've nicknamed Trufflehunter. And finally, I'll describe the case studies, so the measurements that we took of stalkerware and typo squatting and a couple of other different interesting internet phenomena. But I'll start out with how we reverse engineered caching strategies. So we ran this experiment where from a single location, so presumably hitting a single POP, we repeatedly queried each of the resolvers in our list to try and fill as many caches as possible. Then we wanted to observe how the queries were cached, so we plotted their TTLs against their timestamps. The idea is we have this concept called a TTL line, which is our model of how a TTL decreases in a cache. You ought to be able to draw this line with a slope of -1 because it should decrease 1 second per second through every measurement you take. And if you do that and you get a whole bunch more measurements that show up on that line, you can tell they came from the same cache. Then all you have to do is count the TTL lines and you'll know how many caches were filled. When we did this for each of our 4 public resolvers, we found out that they have differing numbers of caches that are visible to users like us. For OpenDNS and Quad9, we found out that they're running a whole bunch of different independent front-end caches, which back onto a bunch of independent back-end caches. And that was kind of the ideal situation for us because it meant that at every POP, we could measure a whole bunch of caches, which meant we could measure a whole bunch of users. Cloudflare, on the other hand, we found out has a shared front-end cache because we only ever saw a single TTL line coming from each of those POPs. So that's probably very efficient from a caching perspective, but from the perspective of us trying to run a measurement study, it wasn't as useful because it meant that at each Cloudflare POP, we could only measure 1 user at a time. And then there was Google, which was doing something interesting. We would make a single request to a Google resolver and find out that it had been cached in a whole bunch of different places, but we didn't see multiple requests coming into that domain's authoritative name server. So we labeled this the dynamic front-end strategy, and we tried to dig into it a little bit more because we didn't understand what was going on. There were so many visible caches here. What we found is that, first of all, previous work had noted this phenomenon as well. As a matter of fact, there was a particularly poetic paper which called these interesting caches ghost caches. And what we found when we tried to investigate was that we think that the TTLs were getting reset in these front-end caches when requests were being copied from back-end to front-end. So if a request came in and missed in a front-end cache, that front-end cache would then load the maximum TTL rather than the TTL that the back-end cache had. So that was great for us because it let us measure about 10 times as many users at every Google POP as we could at any other POP. But after we published this paper, we actually found out that this behavior was a bug. Google got into contact with us after the last IETF meeting to say, oh, yes, we noticed that was happening, that was not intentional, and we rolled out a fix in January. So unfortunately, that behavior is not there anymore. But it was great for the few months while we were running this measurement study. So having figured out how to count caches at public resolvers and how to distinguish between those caches so that we could measure them, we next set up our tool, which is called Trufflehunter. So all that Trufflehunter is a distributed program that runs on Kata's Archipelago project. For anyone unfamiliar with Archipelago, it's a bunch of measurement nodes. I think there's 46 spread across the United States at the moment. And what we had them do was just send DNS queries constantly to every POP they could find across the United States. Once they got the responses back, they would interpret them according to our models in order to estimate the counts of users. And for the purposes of this paper, we used 3 months of data between March and May of 2020. So the first challenge we ran into was how to detect which POP a query was using. And to do this, there are these great, what we call location queries, which are provided as debugging tools by the 4 public resolvers. For Quad9 and Cloudflare, these are chaos id.server queries, and Google and OpenDNS make 2 different TXT records available to people who want to debug stuff. So we ran these once a minute, and we found out to our surprise that the location churn of our measurement nodes was actually usually pretty low. We would see these long stable periods where for hours or days or sometimes even weeks, measurement nodes would keep going to the same POP over and over again. But then they would occasionally go into these short unstable periods where they would fluctuate between up to 3 different POPs for up to half an hour at a time. The next challenge that we had was, well, we had these models that we had reverse engineered of how the caches worked, but we didn't know if they were accurate. So we had to run an experiment to figure out ground truth, so to speak. So we placed a domain that we control into the caches of all the public resolvers we could find by having ripe atlas nodes make those requests. Those ripe atlas nodes were supposed to take the place of real users. Then we had Trufflehunter try and observe that domain, and we counted every request that came into our authoritative name server as representing a true filled cache. So on resolvers with reasonably straightforward architecture like OpenDNS, our error was pretty good. We were pretty close to the ground truth. On Cloudflare, we were reasonably good except for one particular POP where we think there was some routing going on that we hadn't accounted for. On Google, it turned out to be hard to disentangle the effects of this bug that I mentioned from the true number of caches that were getting filled. But we were able to tweak our algorithm so that we were always underestimating rather than overestimating, which is good because recall that our goal in this work is to provide an underestimate, if possible, of certain types of rare behavior. And then on Quad9, we found out something interesting, which is half of the backend resolvers at Quad9 are using Unbound, and Unbound does not respond to the types of queries we were sending, which had recursion desired equals 0. So that means if a request comes into Quad9 and gets cached by Unbound software, it becomes invisible to Trufflehunter. So we can only see about 50% of the caches at Quad9. And then, of course, the limitation of any sort of cache snooping you're ever going to use is that you can only observe 1 user per cache per maximum TTL. So, of course, we're limited by the number of caches we can see at any one time. At Google, particularly for the more popular POPs, we could see quite a few of these because of that bug that I mentioned, up to 8,000 at a time. On OpenDNS and Quad9, we saw about 80 different caches at a time at the more popular POPs and fewer at the less popular POPs. And then, of course, Cloudflare, since it's got a shared cache, we could only see 1 at a time. So once we'd figured out Trufflehunter and had gotten it working to our satisfaction, we started running our case studies and actually measuring the types of rare phenomena that we wanted to see. We had 3 of these, the first of them being stalkerware, and then contract cheating, which is a new type of cheating that people are doing instead of plagiarism, and typo squatting. So previously, all of these were hard to measure for one reason or another. And in particular, stalkerware and contract cheating didn't have any data available about their prevalence. I'll go more into that in a minute. For stalkerware, in case you haven't heard the term before, it does what it says on the box. It's this emerging spyware threat. It's usually installed by an abuser on a target's phone while the target is unaware of it. And it's got capabilities from, recording a target's location to key logging for all sorts of different apps. It can usually log every app you care to name. Some of it can even turn on the ambient sound and video for a device, so it can record the microphone and the camera without the user knowing. And the most insidious of this stuff hides its presence on the target device. So you can go to the list of apps and maybe you see something that calls itself, data backup or Wi-Fi, but there's no icon that's going to tell you this thing is on your phone. And stalkerware is kind of a nuanced problem because it comes in two categories: dual use and overt. Dual use apps are usually marketed for a legitimate or at least legal purpose, like parental control or employee surveillance. And overt apps are usually marketed explicitly for intimate partner violence or IPV. And they're the ones that usually advertise themselves as being undetectable, the ones that hide their icon on the target device. So we downloaded 6 of the dual use apps and 16 of the overt apps and recorded their network traffic to figure out what DNS requests they were making. Now, the thing about stalkerware is that I just told you that there are these overt apps and the dual use apps. Prior work in this space has mostly been done in clinical settings, and it's mostly been done on the dual use apps because that's all that researchers have been finding. It's much easier to do something like install an app that's on the App Store or change sharing settings or something like that. And so all of the work in this space had been focused on that type of stuff, and nobody knew how many overt apps were actually out there in the wild. It was easy to find them if you just Google how to track my girlfriend or something like that, but you hadn't been seeing it in clinical settings. The second challenge, the good reason why you don't see much of it in clinical settings, is by the time someone has gotten worried enough to go to a domestic violence shelter, they've often already reset their device. So there's no way to tell if something has been installed on it previously because a reset has gotten rid of every type of stalkerware we've seen so far. And then finally, the clinics that are doing this often lack technical expertise. So unless they're working with a technical expert, like the folks at Cornell who are doing really great work in this space, they might not know what to look for. So we decided to try and find stalkerware. And of course, what we want to do is not just count the number of domains that are being requested, but count the number of devices that have stalkerware installed. Turns out stalkerware is perfect for this purpose because it doesn't have any user interaction. It hides itself on the phone. So it has to make its DNS requests automatically at regular intervals. That means all you have to do is divide the number of filled caches observed by Trufflehunter by the app's request rate, and you get an estimate of the number of devices with stalkerware installed. So when we did that, the most stalkerware targets we ever saw at any one time are shown in this chart here. We found out that there's at least 5,700 people that are targeted just by the overt stalkerware in the US today. And we think that these results make sense because, the most popular app we saw was the only free one, and the second most popular one we saw was the only one that was available on the Google Play Store rather than from a third party. So we think that validates this technique. It's probably reasonably accurate. We also looked at the stalkerware dashboard visits. A stalkerware dashboard is where the abuser will go to try and look at the data that has been recorded by the app. We found that the popularity of the app doesn't necessarily equal the popularity of the dashboard. We thought this might be because different apps have different capabilities and therefore update at different frequencies. The second case study that we did was contract cheating, which is the new thing. It's the new cool thing the kids are doing these days. There are these services where you pay them a fee and they will complete your homework or your class project, or there are some that will even take an entire class for you. And it's very difficult to detect because they're actually providing original content. So plagiarism checkers don't work. So we had to look for a whole bunch of these websites, which, by the way, are quite easy to find. Not that I am endorsing this in any way, but a quick Google search will find dozens of them. They're quite popular. So we put them into Trufflehunter, and we found out that over the 2 weeks we were running this particular study, some of these services were decreasing in popularity. And we thought, that might be because schools are letting out for summer break around now, and the market for contract cheating is decreasing. So it might be fun to look into that further in the future. And then finally, we wanted to look at typo squatting, but the typo squatting domains that we had were I think about 3 years old. So we threw this in expecting to see that none of these domains were actually getting requests anymore, but we were wrong. Turns out some of them are getting up to 80 requests per day, which was interesting because the conventional wisdom about typo squatting is that these domains cycle through very quickly. They get blacklisted very quickly, and then spammers or phishers will move on to new domains. So it was interesting to see that so many requests were still coming in. So our takeaway from this project is we don't think that cache snooping on public resolvers actually presents a privacy concern, because there are millions of people that are using every single POP, and we don't think it's possible to de-anonymize. I shouldn't say that it's impossible, but we think it is prohibitively difficult to de-anonymize anyone who has put a domain in cache. But it does provide this really useful measurement technique that lets us measure these dangerous phenomena like stalkerware that we can't measure anyway else. There's also some phenomena that we haven't had a chance to look into in too much detail, like hack for hire services that we would really like to study in the future. So to conclude, we found that public DNS resolvers enable us to use cache snooping as a privacy-preserving measurement technique rather than as an attack. We think this is a really valuable measurement technique and it shouldn't be disabled. And we used it to find non-trivial lower bounds of the prevalence of certain hard-to-study internet phenomena, such as stalkerware, contract cheating, and typo squatting. So Trufflehunter is open source, although I have to admit we found 1 or 2 bugs in the open source version over the past couple of weeks. If you want to check it out, you can go to this link at the bottom of the slide. And I'd like to thank you for your attention. Anyone got any questions?
Thank you, Audrey. That was a very interesting presentation. I would like to remind the audience to please fill the poll. This would be your only chance to rate the talk. And now we are ready for questions. I have a first question from Joe Abley. And his question is, did you consider whether cache prefetching might be happening and prolonging the existence of particular names in caches? This seem like it might inflate the apparent number of clients requesting of a particular name.
We did consider that, and we ran about a month's worth of experiments trying to make sure that no prefetching was going on for these domains. I think these domains were unpopular enough that no prefetching was happening for them.
Thanks, Audrey. We have one more, I think, observation from Paul Hoffman. Paul Hoffman is saying, thank you for focusing on stalkerware. It's incredibly pernicious, so having real data on it is valuable. Thanks, Paul. Since there are no questions, I had a question, Audrey. Do you have planned to, just the way there is a tool like DNSWiz that Casey, who is following you, has created so that other people can use the tool to evaluate domains? Do you have plans to not only open source it, place it someplace on server somewhere where people can then use it to actually search for names which are trademark type of somebody is infringement on trademark type of domains? People can look for those in addition to all of the use cases that you mentioned.
So you're asking if Trufflehunter is available for people who want to look for trademark infringing names? Yes, yeah, that should be the tool that is available at this link here. If you want to try it out for yourself, it'll just tell you how many caches are filled with that particular domain.
Okay, sounds good. Thank you. Okay. We have one more question from Daryl. It's a comment rather. is saying, agreed, this seems fruitful for stalkerware, etc. However, do you believe there really is anonymous standing for a resolver in Japan for domains of small firm / college in New England?
You're asking if there is a risk of being able to de-anonymize a user if, for example, they've hit a Japanese resolver and asked for, something that could only be found in New England. You think that you could de-anonymize whoever has done that way?
Yeah, I think that's what is Daryl's question.
Okay, so you would need to know that there is somebody in Japan who is trying to find something related to New England, and we thought that for the domains, specifically for the domains that we are looking for, they're generic enough that there's no link that we could look for to find that out.
Okay, thank you, Audrey. We have one more question from Andrew. He's asking, are details of stalkerware URLs available for resolver operators to add to their threat feeds?
This is actually a question that's come up a lot in the past few days. It actually has a bit of a nuanced answer, which is, yes, there are threat feeds that are available, but we need to be a little bit cautious about what we do to block these kinds of apps, because there is a danger that if you block this app and the abuser thinks that the target has uninstalled the app, if they interpret this app not working as the user having uninstalled it, it can be a problem. It's actually one of the things that often causes a situation to escalate into violence. And so the people who are real experts in stalkerware, which are mostly the people at Cornell University who really dug into this problem, they don't necessarily recommend doing that in all cases. So what I can tell you is there is a group, I think it's called eChap. They're a French organization that works on the problem of technology and its use in intimate partner violence. And they have a threat feed, which I think they have provided to Quad 9, which I think would be a better choice than our own threat feed. So I can get anyone interested in contact with them.
Thank you, Audrey, and thank you for all the questions. I think we are right on the dot. At this time, I would like to welcome Casey, Deccio, to give us a peek into the DNS cookie jar and analysis of DNS cookie use. On to you, Casey.
All right. You can hear me okay?
Yes, I can hear you and I can
Great.
see the slides. Thank you.
Perfect. So let's see. So I wanted to talk today about our study of DNS cookies. This is work that was done at Brigham Young University with one of my students, Jacob Davis. And so I'll go ahead and talk about the motivation behind our work and then what we did in terms of our measurement study. So first of all, and I know many of you are familiar with the DNS already, but this sets up a stage for how we performed our measurement and the different perspectives that we're looking at when we did our measurement with regard to DNS cookies. So we're really talking about two client server pairs in the DNS. We have the stub to recursive resolver communication, and then we have the recursive to authoritative communication. Okay, and both of those run over UDP primarily. Obviously, we have many other transports today, including DNS over TCP, DNS over TLS, but at least according to the original standard and in a lot of cases, the default, especially for recursive to authoritative, we're still using UDP. Now, when we talk about identity in the DNS, because we're using UDP primarily, or at least using that as our model, there isn't identity built in. And so the two things that we look at are, first of all, server identity. So when we look at a cache perspective, we're querying the victim who's querying a server, and this could be from the stub to recursive or from the recursive to the authoritative. You query a server and then you get something back, and you sort of have to make some assumptions that it came from the server, but in reality it might be an attacker. Think back to source port randomization as one example of how this can sort of defeat UDP, okay, in traditional DNS model. And then the other model here is looking at client identity from the server perspective. How do you know it's actually coming from the client that's actually requesting something, the legitimate client? In the case where it's not, it's actually what we refer to as a reflection attack, where these packets are coming in, claiming to be from some victim and being reflected onto that victim. Okay, so DNS cookies came into play. They took their time through the standards track, and they were standardized in RFC in 2016. And so the idea behind it is that now when a client initiates a communication with a given server, then a cookie, and this is implemented as a DNS, an eDNS or extended DNS option, they send a cookie in there, which is basically just a value that the cookie sends to it that expects the server to send back to it. But in addition, when the server sends something back, it doesn't just return the cookie that the client sent to it. It also returns its own server cookie that expects the client to send back in subsequent communications. And what that does is it basically allows both parties to mutually authenticate each other's identity, and so that helps with the identity problem. And off-path attackers can't see that, and so that's the way cookies work. So what we wanted to do then is measure where are we at with DNS cookies. I mean, they've been standardized for 5 years. We wanted to see sort of some of the popular DNS servers and how they're implementing them, if they are at all. So we have 3 data sets that we're using. First of all, we're looking at authoritative server support. And so we use 2 categories for that. The server's authoritative for top level domains, and then the server's authoritative for the Alexa top 1 million. Okay, and so the resulting IPs, there are about 157,000 Alexa IPs and about 6,600 top level domain IP addresses that were the servers that we tested. And so because eDNS is a prerequisite, we found that in the case of authoritative servers, just over 98% supported eDNS, which is good, but about less than 30% fully supported cookies. And what do we mean fully supported? We actually checked not only were they, did they send back in the full protocol, to the full protocol extent of, hey, I see your client cookie and I'll add to it a server cookie, but also were there any servers that were just sending back a client cookie, which really isn't a thing, but you could say in theory it still has some sort of protection for the client in terms of server identity. And so there was a small percentage here shown in orange of Alexa IPs that were actually just echoing the client cookie, which was sort of interesting. But in general, in terms of full support, less than 30% were fully supporting cookies. We also wanted to look at support at recursive resolvers. And so we actually did a search of all open resolvers in the IPv4 address space to get a set of recursive resolvers. And we discovered about 1.9 million in our scan. And we found that only about 70% of those recursive resolvers supported eDNS. And in terms of full cookie support, we were about 17%. And again, there was that sort of orange area here where we saw this sort of half support where a server would echo a client cookie, but didn't send its own server cookie. Okay, so we also wanted to look, and if you look down, and by the way, at the bottom of the screen, we're sort of showing a legend in terms of the sorts of things that we're looking at. So in this case now, we're looking at recursive server support as a client. And so not as a server side, but when they query our authoritative. So what we did was we set up some authoritative servers over which we had control, and we issued queries to the recursive resolvers such that they would query our authoritative and we could analyze their queries. Okay, and we saw only about 10% support in terms of, again, client-side support from the recursive resolvers. So we're sort of decreasing in our support level as we continue our perspective search here in support of DNS cookies. Now, we wanted to look at enforcement because that's sort of, adding teeth to the whole thing here. And so the first thing we did was we wanted to set up an experiment in which so again, this is looking at recursive resolvers, and they're getting back responses from our authoritatives in which we're, let's see, we made sure that they had full cookie support, and then we're responding back with no cookie or with an incorrect cookie. And we found that 85% of clients, they just behaved normally when we saw that they were sending cookies, so they supported DNS cookies. But when we stripped out the cookie on our response, after we'd previously sent them a cookie, so they knew we supported it, they just go ahead and behave normally. And only 20%, that was when we stripped out the cookie. When we sent an incorrect cookie, only 20% were behaving normally. So there was some hope there in terms of that. But barring other measures, these numbers, these caches that behave this way were more susceptible to cache poisoning, at least in terms of use of cookies. Okay, and actually this is in direct violation of the specification. If the client is expecting the response to contain a cookie, and it was because we'd previously sent them one, and it is missing, then the response must be discarded. Now we wanted to look in terms of enforcement from the servers. And so, so this is on the server side, both in the recursive model and the authoritative model. We were playing bad clients, basically. So instead of us returning the server cookie to servers that we had previously sent cookies, so they knew we played well, we supported DNS cookie as clients, then we sent them a packet with no cookie and then with a fake cookie. Now, according to the specification, a server can either discard the query silently, which is sort of the the most forceful, or it can respond with a bad cookie error code, which basically says try again, but give me, return back the cookie that I just gave you, or it can respond normally. And what we saw is more than 99% respond normally with even when we sent a query with a missing or a fake cookie. Now, again, there's some sort of varying degrees of compliance with the RFC here in terms of how they might do it, but 99% were using the least restrictive approach. Okay, one last thing we looked at sort of in closing here, we wanted to see what else we might be able to find. And so there's this notion of what's called dynamic server cookies. And part of what's included in a dynamic server cookie is that the server, the cookie itself includes a clear text timestamp along with a hash and a nonce. And so what we did was we sent 60 queries to each of these servers that we knew supported DNS cookies. And then we collected all these cookies so we could further analyze them. So we could identify dynamic cookies, first of all, and see who was using that model versus some other model, as well as other interesting behaviors. And this is what we found. So first of all, we identified a dynamic cookie by saying, okay, if that embedded timestamp in the cookie that they sent us was within a window of 1 hour in the past and 30 minutes in the future, then we said, yeah, this is probably using dynamic cookies. And so we saw that in terms of authoritative servers, both in terms of the TLDs and the Alexa DNS servers, 99% were returning at least one dynamic cookie. In terms of the recursive servers, 83% returned at least one dynamic cookie. So fairly high. A lot of people are using dynamic cookies. Here's the interesting part. So what we did was we actually, for each of these values that came back as a timestamp, we subtracted that from the current time and took the absolute value of that. So we ended up with a number for every single query. So in this first example, we'd say, oh, okay, 11112. They were all fairly close. We'd say the timestamp of these cookies, the machine that sent the cookies was fairly accurate consistently across all these queries. And then we'd see something like this, 75 seconds off, 75 seconds off, et cetera, between current time and again, the timestamp embedded in the cookie. And we'd say, oh, those ones were out of sync. Okay, they were greater than 60 seconds. And then we saw this sort of behavior here where we'd see 1111 75, 121 75. And so it was this mixed, accurate, and out of sync. And what we found was this was sort of representative behavior of if you queried something with the front end and it was actually getting its cookie from a back-end server. And 4 of those, in the case where there were 5 back-end servers, 4 of them had an accurate clock and 1 that was out of sync. So here's a breakdown of some of the numbers that we saw. We only saw this mixed, accurate, and out of sync, a very less than 1% of the time, at least in the Alexa list, but some of the interesting behaviors. I'm just going to wrap up here so I have some time for questions. One other thing we saw was interoperable cookies. They begin with a special byte value and they're dynamic, as we explained before, with regard to their timestamp. We saw only about 4.2% of auth servers were using interoperable cookies. Slightly higher amount in recursive servers, but we saw about 6.5% of servers using a mixture of interoperable and non-interoperable, which was sort of defeats the spirit of interoperable cookies. So kind of interesting. All right, I'm not going to talk about these right now. I can talk about more of those in sort of Q&A if there is any, but just in summary, we saw only 15% of clients were enforcing cookies properly, and less than 1% of servers are enforcing cookies. And one idea to maybe help with this is to sort of advertise intended use of cookies. So that's all I have, and I'm happy to take some questions.
Thank you, Casey, for the presentation. I sense a DNS cookie flag day or something in future. We have a comment from Tian Ho Chi. The comment is, we, Google Public DNS, are experimenting DNS cookies to enable and send them to authoritative name servers recently. An interesting finding is that the percentage of real traffic DNS cookie can protect will be significantly lower than the percentage of name servers. For those 30% name servers that fully support DNS cookies, they account for approximately 5% of the outgoing traffic.
Yeah, it's a great comment. I haven't studied. One thing we didn't do was actually look at, and that's something you always want to do, is look at, okay, well, how significant are these servers that support it or don't support it? What kind of an impact are they having? And you could also say, what's the difference between noisy servers and truly significant servers otherwise? Because I don't think noisy necessarily means significant. There are different ways of measuring that, but that's a great question and comment, I guess, in terms of one way to look at that, which we didn't look at in our study.
We have one question from Ali Reza Saleh. You can unmute yourself and ask your question.
Excuse me, I think that I just mistakenly put in the raise and I don't have any question. Thank you, Krishna, for that. Thank you.
No problem. We have a question from Joe Abley. Joe, you can unmute yourself.
Hi, Casey, it's Joe here from PIR. So it occurred to me, you use the Alexa source list, popular websites, to try and find name servers, authoritative name servers to look at. And it seems to me those are more likely than the general random set to be hosted on the kind of enterprise server that uses clusters. If you use a cluster which is, has autonomous sort of origin servers behind whatever load balancing technique they're using, then the chances are that they don't have, or they may not have, a way of sharing server cookies between different origin servers. So it's possible, it seems possible that you've just chosen a sample set of servers, and the Google comment is similar about most popular servers that are just implemented in such a way that server cookies are kind of impractical to support, and or at least not implemented and shared between those origin servers. So maybe that's biasing your results. Maybe there are more servers that support DNS cookies correctly than you're seeing, and the ones you're seeing are the ones where it's just architecturally difficult to support them.
Yeah, that's a great point, Joe. And I don't have the answer to that. I mean, we did see some, and by the way, when we implemented DNS cookies on DNSFizz, I don't know, close to 2 years ago, that was one of the first things that started jumping out at us as we started seeing these errors that I didn't even expect, sort of like, oh, by the way, we'd seen cookies from the server and now we're not seeing them. Sort of those weird cases that, maybe a lot of people didn't expect. And in part, we're not seeing those also because cookies aren't being enforced, as we saw in some of our research. And that's, that's just known, is that they're not being enforced yet. So the short answer is probably yes and no. I mean, we probably did miss some stuff because people were like, let's just turn it off for now. But there are others that probably just sort of unknowingly doing it because they're not being enforced in sort of the ideal way at this point. But that's sort of my best answer for now, but it really needs more looking into.
Yeah, maybe the phenomenon you saw of just echoing back the client cookie but not sending a server cookie, maybe that's someone who really wants to support cookies but can't share the server cookie across the different origin servers, so they're doing the best they can.
It could be, or and I know Brian has another question here. Sorry, Pallavi was going to read it out probably, yeah. But he asked about that. He asked about that in here. It says, do you mind if I read it, Pallavi?
Yes, go ahead.
Okay, sorry. It says, did you attempt to distinguish blind mirroring of EDNS options rather than actual cookie parsing? And we actually didn't look at that specifically, but that might have been what we were seeing when we saw the client cookie only. So that's something we'd have to go back and look at as well. So that could be Joe. And sorry for overstepping my my bounds there, but I think Brian's question had direct relevance to Joe's question. So
we have one more question from Mark Andrews. Mark, you can unmute yourself.
Yeah.
Sorry, Mark. Go ahead, Mark.
I did click unmute. Okay. I did. I tried. Mine's cookies were done very conservatively at the beginning because we were doing it into a world without any cookie support before the RFC was actually written. The echoing of cookies you'll find is Microsoft servers prior to the first that were deployed prior to the DNS flag day fixes that Microsoft, the first flag day fixes that Microsoft did. They do their servers, Microsoft servers were just echoing back the eDNS option. And when you don't send back a server cookie, the server is supposed to actually respond to you as if you're a different client. This is how you differentiate. This is how the server differentiates clients behind a NAT. So yeah, you don't expect the server to not answer when you don't have a server cookie coming at it. Binds by default doesn't force a cookie before it responds, but you can definitely turn it on in named.conf. I do that and it works well enough. But yeah, I don't know whether we want a poll, but would people be happy if we made bind always require a server cookie if it saw the client supports cookies? That'd be an interesting question. Well, we'd like to see. I suppose we'd like to see the answer to, because we can change the default easily enough. It's about 10 seconds work.
Yeah, Mark, by the way, these are great insights from you know, a developer and protocol specialist here in this area, of course. I appreciate those insights. I'll maybe say two things to you know, to respond to your comment and question there. One thing is, with regard to our experiments, we took a lot of liberties, and we weren't looking necessarily at the way things were, you know, necessarily implemented. We just wanted to see from an attack model what would happen if we did certain things. But we know there was different intent, sometimes both in the implementation and in the protocol specification. But again, we sort of said, let's lay that aside and look at what could happen. And with regard to your second, you know, your second item, what should we do? And I'll wrap this up really quick, Bobby. I just say, I think we can do more experimentation and find out, but I think a lot of this can be measurement driven and data driven. And maybe we can talk more offline about that, Mark.
Thank you, Casey. Sorry to cut you off. Now, I would like to welcome Matt Luckie to talk about machine learning router hostname patterns. On to you, Matt.
So yeah, so this talk is about machine learning internet router hostname patterns. My name is Matthew Luckie. I'm with the University of Waikato. And just briefly, the talk is about trying to extract meaning from DNS hostnames automatically and learning to do it. The specific application that I'm discussing, extracting information from router hostnames. So in this slide, I have 6 different routers operated by Hurricane Electric. And we can see that the operators of Hurricane Electric have annotated these host names in different ways. And I've done this because it helps them and third parties contextualize internet routing behavior. So we can see, for example, that Hurricane Electric embeds a router name or a string that is unique to each router, but it is in common across each of the interfaces on that router. We can see within that string, they have embedded a geolocation code that indicates roughly where a router is physically located, be it Fremont, Atlanta, or Ashburn. We can see that they've embedded a string identifying the speed of the interface involved, if it's 100 gigabit Ethernet or 10 gigabit Ethernet. And we can see also that for the routers that belong to other networks that interconnect with Hurricane Electric, that Hurricane Electric have embedded a string that identifies or names the network involved. Finally, sometimes Hurricane Electric also embeds the autonomous system number or ASN of the interconnecting party. So the goal of this particular piece of work is to automatically build or learn regular expressions that extract different features from these host names when these features are present. So the tool that we've created, Hoiho, what that does is, given a training set, attempts to learn a regular expression that reliably extracts a given feature from the host name. So there are a number of challenges to this piece of work. The first one is that there is significant variation in the ways in which operators label or create their host names. Each operator has essentially its own dialect. So for example, for these 3 routers, and these are all border routers with host names assigned by different networks, each of those networks has their own convention. So for example, GTT will embed an autonomous system number into the ASN for those border routers, whereas Telia and Cbone will embed the interconnecting party's name, in this case, Edgecast or PCCW. Beyond that, even for geolocation, each of these operators can choose their own geolocation codes. So GTT happens to use the well-known IATA airport code for New York City, but Telia and Cbone have made up their own geolocation code. And in fact, for the next router down, that's physically located in London. LDN is an airport that is not located in the UK. A second key challenge is that there's almost no ground truth around to train a model. So what we rely on instead are heuristic labels that have been heuristically assigned by different algorithms. The data set that we use is the CADA Internet Topology Data Kit, the IDDK. And this data set contains sets of routers where these routers, the different interfaces have been analytically inferred to belong to the same router, which host, the host names that belong to the same router, as well as which AS owns each router, also inferred using heuristics. And of course, the data set also contains pointer records. So just as an example of how the algorithm proceeds, how it builds these regular expressions automatically. So for the ASN cases, where in this case Equinix is embedding the ASN of the router that with this particular host name, what it does is it has a set of training ASNs that are inferred heuristically, and these usually aligned with the host name, but sometimes either the host name is stale or the training ASN is because it's inferred is wrong. But what it does is, given where it sees a number, it will try to build a regular expression that extracts that number for each individual host name using that host name as an example, and then apply it to the full set. So in this case, it's built 4 different regular expressions that each extract from a portion of the routers. We can see that 3 of the regular expressions are very similar. So what it will do is then merge these regular expressions together automatically to build a regular expression that matches more of the host names. It will refine the regular expression to build some specificity into it. And then when multiple regular expressions are required to cover the different cases within a given suffix, will build a set and suggest that as the regular expressions to use. So the tool that I've talked about, HoiHo, that is publicly released as source code, as well as some web pages published at CADA that contain a set of inferred regular expressions that are free to download, as well as web pages that demonstrate how each regular expression has applied to the training data. Particularly for this talk, I'd be interested to hear if there are if you believe there is scope to apply these techniques that are focused on a relatively narrow domain, router host names, to other types of host names that might be present in the DNS. I'm welcome to take questions.
At this time, I would like to remind the audience to fill the poll that would pop on your screen. This is the only chance to rate the talk. And please go ahead and ask your questions. We have a few minutes for questions. I don't see any questions coming in, Matt. So I had a quick question just to get it started. Is there any work on standardizing some of these host names, or is it historically every manufacturer would do it based on themselves?
So not that I'm aware of. What I have heard is that some operators might have inherited or managed to obtain scripts from other operators that they have used internally to populate their host names. But as far as I'm aware, there is no standardized way to construct these host names. So it's up to each individual operator to decide what they're going to put in these host names and how they're going to structure it.
Okay, thank you. We have a question from Wes. Wes, go ahead and ask your question. You can unmute yourself.
Hi, thanks. It looked like really good work. I liked it a lot. We've done similar templatizing stuff for other sets of stuff that, obviously brings me to my question of, have you tried it with any other data sets like host names for, other things besides routers? I'm trying to think there are, data centers and things like that that have, end hosts for computing clusters and things like that. Have you applied it to anything else or just routers at this point?
So just routers at this point, but I'd be curious to understand if there are other, other places where this technique would be useful. But roughly, sort of what it needs is some, well, it needs the host names obviously, but also some indication of, or some feature or some label, and it can also, that label can be inferred heuristically to that we're trying to sort of match up the two of them. So that's sort of what it needs. Yes.
Thanks, Matt. We have one question from Eric Klein. How much diversity, alternatively creativity in these patterns was found? This is
there's, well, lots. I mean, the short answer is if you can think it, it's there. And even within, a given suffix, often these things are also manually entered, and we even, see things like typos and stuff. So there's a lot of diversity. So there's all these sort of edge cases involved, and sort of, I guess, things to keep in mind when sort of building the algorithm that tries to build in these regular expressions automatically. But yeah, there's lots of diversity there.
Thank you, Matt. Jacob, I see you have a question, but please go ahead and ask your question on the workshop channel because we're out of time for questions. Thank you, Matt. And now we are going to have the final presentation for this session. I would like to welcome Yoshitaka Aharen-san to talk about evaluation of anti-DDoS features in full service resolvers. On to you, Aharen-san.
Hello, this is Yoshitaka Aharen. I would like to present an evaluation of anti-DDoS features in full service resolvers. Okay. And first, let me introduce our environment. We JPRS operates at TLD.jprs as an around the platform. Please find details in our website. We have 2 presentations in 2017 and 2021 of the results using the platform. And at this time, we conducted an experiment of anti-DDoS functionalities implemented in full service resolver implementations with Japanese domestic ISPs. And I am going to show the results and some findings. First, let me talk about the purpose of the evaluation. Our purpose is to evaluate anti-DDoS functionalities with DNS operators of the ISPs. We try the functionalities in an evaluation environment and give some feedbacks to software implementers if possible. We tried 2 implementations. One is bind 9 and the other is unbound. We tried fetch limit or rate limit feature and sub-stale and sub-expired feature. What we didn't try is the 2 features. NSEC aggressive use was .jprs is signed with NSEC3 opt-out, so we could not try this. Also, DNS cookies were not tried because an update to RFC 7873 was ongoing in DNSOP at the time of evaluation. Next, I would like to introduce participants. This is a joint research effort with 9 domestic ISPs. We conducted an experiment with regional and nationwide ISPs, which is CNCI and NCOM, FreeBit, Hotnet, HTNet, OptEdge, OTNet, QTNet, and SoftBank. And they operate full service resolvers for their customers. We cooperated with DNS operators in the ISPs. The purpose of each company's participation is to verify countermeasure technologies to ensure stable operation as a full resolver operator in the event of a cyber attack. Next, I would like to introduce the evaluation scenario. We set up a full service resolver with both fetch limit and sub-stale enabled. And suppose a situation that an authoritative server is under DDoS attack, which is RD to 2020 demo2.jprs, which is under our TLD.jprs. It is in our real environment. We set up an authoritative server on the internet and generate random subdomain queries to the full service resolver. And fetch limit will suppress outbound iterative queries. Then the authoritative server becomes not responding because of a massive query from the others. DDoS traffic from others increases and the victim server is not massive. So actually it is simulated by dropping inbound queries. So in that situation, sub-stale will use the stale cache to answer queries, and legitimate queries still can resolve the domain name. Then the victim switches to another DNS provider. The server are massive enough to absorb DDoS traffic, so they can query all the traffic. Actually, it is simulated with changing delegation in the parent zone to another NSR set. However, the stale cache entry in full service resolver under test is still used. The full service resolver under test answers with the stale cache, and after flashing the cache, fresh data will be returned. That's the evaluation scenario, and we tried this scenario entirely. And the results are in this slide. The combination worked as expected with Unbound. Rate limit restricted the number of iterations to the authoritative server. And full service resolver continues to respond with cached answers even after the authoritative server becomes not responding and the TTL of the RA set expired. That's the sub-stale. But bind 9 worked differently than expected. Fetch limit restricted number of iterations to the authoritative server. This is expected result. However, it responds with sub-fail after the authoritative server becomes not responding. We tried to check the content of the cache with rn-dumpdb command, and it shows there is stale cache entry, but sub-stale does not work expected. So, in addition to the above, stale cache may be used unexpectedly. For the evaluation, maybe we should wait some time after changing the delegation to see what happens in the scenario 3. And there are some comments from the DNS operators, which is sub-stale in bind 9 did not work as expected, which is explained in the previous slide. And there is a concern on the stale cache, and it may cause name resolution failure or getting all the contents even after the delegation or zone contents change. And after the experiment, we realized that it can be controlled with infrahost TTL option.
This is a timekeeper. There's about 1 minute until Q&A.
All right, thank you. And okay, I will go into the next slide. So we sent some feedback to the implementers. They generously gave us a response. For ISC, we told that fetches per server or fetches per zone interface still after enable option. It cannot be used in combination. And there already was an open issue, which is an issue number 1712. They confirmed the behavior seems to be wrong, and it has been fixed in 9.60.13 release, which is change of entry 5573. And to NLNet Labs, we told that a concern on the default value of sub-expired TTL is set to 0, which is different from suggested in RFC 8767. They confirm it is a good idea to change, but changing it may be complicate operators. We agree with it. And the conclusion, we evaluated anti-DDoS functionalities with DNS operators of some Japanese domestic ISPs, and we found some implementations did not work as expected. And we gave some feedback to the implementers and got positive response. Finally, I would like to express thanks to ISC and NLNet Labs for handling feedback from us and participating ISPs listed in this slide. Thank you.
Thank you, Aharen-san. We don't have any time for questions at this time. Audience, please go ahead and fill the poll. And if you have any questions for Aharen-san, please ask them on the workshop channel. Thank you. And on to Keith for wrapping up this session.
Okay, thank you, Pallavi, and thank you, Manu, for being session chair and timekeeper for that session. And thank you to all our speakers. We're now going to break. Before we do that, I would just like to thank the sponsors of our workshop this time round. It's Farsight and VeriSign. We're going to be breaking for 85 minutes, so we will restart at 4:30 a.m. UTC sharp. If you want to hang out with people socially during the break, you can use a spatial chat platform. You'll see the details of that on the rolling slides. I see there's quite a few people in there that have grabbed the best seats already, so we'll see how that goes. That's basically it. See you in 85 minutes time.
Welcome back, everybody. Please have a seat. We're going to get started with session 3 and 4 of, I guess, this afternoon for some people. DNS-OARC 35, day 1. Before getting started, I would like to thank our sponsors, Farsight and VeriSign. I am Manu Votel, and I will be chairing this afternoon sessions, and I'm joined by William Torup, who is going to be the timekeeper. Without further ado, let me introduce our first speaker, Sudheesh Singanamalla. He's going to talk about Oblivious DNS over HTTPS, or a practical privacy enhancement to DNS. Sudheesh, whenever you're ready.
Perfect, thank you. Hi, everyone. Thank you for being here today. I'm Sudheesh. I'm a PhD student, a second-year PhD student at the University of Washington, and I'll be presenting the feasibility of a new privacy-enhancing DNS protocol called ODoH, or Oblivious DNS over HTTPS. This was a part of my internship work at Cloudflare over the last summer, and it would not have been possible, made possible without all the incredible collaborators. And I'm very excited to actually be representing all of them in today's talk. This work has recently been accepted to the Privacy Enhancing Technology Symposium 2021. So as a quick introduction, and most of you would already know, DNS is the domain name system and is really the foundation of the human usable internet today. And it kind of responds to client queries for host names with corresponding IP addresses and any records that it has. Traditionally, the DNS protocol is not encrypted and it uses UDP. There are other variants which exist, but UDP continues to be a majority of the traffic that is received by the public recursive resolver that Cloudflare operates. And the usage of non-encrypted DNS kind of leaks user information to network operators, to on-path adversaries who are observing the network, and even active attackers who are trying to modify the request from the client or the response from the resolver. To overcome some of these problems, there have been recent efforts to secure DNS using DNS over TLS, DOT, or DNS over HTTPS or DOH. And these have been gaining popularity and have been integrated into various web browsers, operating systems. So these protocols protect the client traffic from being observed by onlookers or being intercepted and changed by on-path attackers. But a problem kind of still remains. The resolver operator can continue to associate which client and their IP address and build a profile around their browsing pattern. So over the last few years, we've actually seen, as a research community, lots of active measurement research trying to understand and measure the impacts of encrypted protocols like DOH or DOT. And many large-scale measurements have shown that the performance of encrypted protocols vary by the choice of the resolver, and it does not significantly impact page load times, and it improves user security. So there have also been various attempts to improving page load times by doing DNS prefetching. But while DOH did kind of improve the security of DNS queries for clients, it also received a lot of criticism about the small number of publicly available resolvers, essentially centralizing the internet and giving these organizations a lot of control. These resolver operators can also associate the client queries with the client IP addresses and use the IP to geolocate the client. So to maintain privacy guarantees, some operators like Cloudflare actively purge this data that is exceeding 24 hours and give their users a privacy policy-based guarantees. But bringing together so many organizations to agree to a common set of privacy practices to maintain user privacy, it requires a lot of explicit negotiation and effort. And Mozilla, for example, has been actively doing a lot of work with the TRR program and does frequent audits before a DoH service can actually be configured as the preset default of the Firefox browser. And some users might be comfortable, might find this idea of a policy-driven approach to be okay, but these are difficult to enforce and are really time-consuming, and making users kind of want a system that can technologically guarantee their privacy. So in this talk, I'll kind of focus on the privacy critiques and the ability for resolvers to be able to create a profile. And that's exactly where the Oblivious DNS over HTTPS or ODoH kicks in. So at a high level, there are three main components in ODoH. The first are the clients who prepare a query for which they would like a response. And the goal of the clients in ODoH is to be able to successfully send encrypted messages and receive valid responses to decrypt. And in the process, be able to identify if there are any malicious actors or take any corrective actions as necessary. The second is a proxy instance whose main role is to relay the encrypted queries from the clients to and from a target, while removing the IP addresses of the client who's speaking to the proxy. And the third is the target instance, which receives the encrypted query from the client, and it decrypts it and obtains the DNS response for the query. And the target's role is to then prepare the encrypted response and send it back to the proxy with no ability to identify the client by their IP addresses. At a high level, the design of ODoH is similar to that of DoH. It kind of builds on it, but it injects this intermediate proxy node, which terminates the client query queue in this diagram and performs the query on the client's behalf. And the guarantees for privacy, however, make this slightly different from a proxy DoH variant, where a client's DoH query can be terminated and performed by the proxy. And the main goal of ODoH here is to prevent the recursive resolvers and the ISPs running such resolvers from being able to link clients to their requests. And the security model here, it builds on the premise that the proxy and the targets actually do not collude. And that's a critical part of the design. So clients need to choose proxies and targets such that they're not operated by the same entity, or they're not known to be colluding organizations. So we assumed the extended DoH adversaries who have this ability to create, drop, and modify network messages, and also give them the ability to compromise TLS sessions in our analysis of the security of this protocol. And practically, colluding adversaries on various network links who can decrypt the connection to read any of the message contents, they can create associations or correlations between the encrypted query and the encrypted response. And this is also true if the resolver secret key is compromised. So in the ODoH protocol, the client encrypts the DNS query using a hybrid public key encryption scheme and a validated public key from the target resolver. And it sends a query with an encapsulated symmetric key from an authenticated encryption scheme to a proxy instance. There are various ways in which the clients can actually learn about these services, and they validate them using DNSSEC, or they can actually look for conflicting keys for the same resolvers. So in ODoH, the proxy instance can see the IP address of the client, but not the contents of the DNS query. And it forwards this message to the Oblivious target, which decrypts the query and decapsulates a symmetric key, and it obtains the response from the resolver. And the response is encrypted by the Oblivious target using the symmetric key that it decapsulated. And it is sent back to the proxy who sees the message, who sends this message to the client and actually can't see this message other than a bunch of encrypted bytes. So in this process, the target only sees the DNS contents and not the actual client's IP address. So we often say that the target and resolver as independent entities, but this need not really be the case. Ideally, in practice, for performance reasons, the Oblivious target and the recursive resolver could be co-located. And this avoids the additional network messages that is sent between the target and the resolver. But it is still possible to maintain these as individual services without any service co-location. So with the understanding of the protocol in place, there were actually three main research questions which interested us. What is the impact of ODoH on the DNS response times? And how does using ODoH actually affect page load times and any user experiences? And also, how does ODoH compare itself to other privacy enhancing protocol variants that are out there today? And this kind of helped us understand what the cost of privacy is for the user while maintaining the security guarantees provided by encrypted DNS protocols. And this slide, it summarizes all our results from the measurement study, but I'll leave this here so that you can get back to it, and I'll go into detail for each one of these results. So for the measurements that we did in this work, we implemented and deployed the Oblivious targets and proxies using Google Cloud and a serverless platform on Cloudflare Workers. And we physically separated the Oblivious target instances from the resolvers, and we randomized the query that we used in our measurements. So we used 9 Google Cloud data center locations to do this measurement, 7 across the US, 1 in Montreal in Canada, and 1 in Sao Paulo in Brazil. And there are 10 client instances that are running at each one of these vantage points, and they're performing an experiment sending DNS requests at a rate of 15 requests per minute. And the average bandwidth for all the clients that were running on a single core processor were 480 megabits per second, but this was never really stressed out or maxed out.
Sudheesh, this is the timekeeper. You have 5 minutes until Q&A.
Yeah, thank you. So yeah, I'll try to go a little quicker. And the clients actually perform these DNS response time measurements, and they choose pairs of available proxies and targets. And so by choosing a low latency proxy target pair for the measurement, which is the orange line that you see here, we find that the average query response time improves by 22.8% compared to choosing only a low latency proxy. And this kind of hints towards the fact that having an intermediate proxy that is on the same network path to the target will actually improve the response time performance while maintaining privacy. This then brings up the question of connection reuse, right? And connection reuse is this optimization that can enable clients to improve their performance by at least 48% at the median. And it avoids unnecessary TCP and TLS handshakes. But the reuse of the connection could leak some client identity information, but it still does not leak any information about the query or the responses by itself. So in the experimental setup that we had, we kind of evaluate for the worst case performance and incur this additional network latency between the target and the resolver. But if you see here, the target instances, which are located in Google Cloud and performing queries to 3 public resolvers randomly, have faster response time from Google DNS because of the potential co-location within the same data center compared to other services. And integrating the Oblivious target into the recursive resolver can reduce this network latency to that of a cache hit. So this is what we've engineered into a public resolver that's operated by Cloudflare as a public service for anyone to use today. And to understand the performance of ODoH, we kind of compare this to other protocols offering similar privacy or security guarantees and use DoH as the baseline protocol, which is here on shown as the blue line. And the DoH over Tor is this variant of DoH, which provides both security and privacy guarantees, in addition to some stronger anonymity guarantees. And this is the orange line that you see to the extreme right. And when compared to ODoH, that's in green, we noticed that ODoH with like no service co-location kind of achieves this interesting position roughly in between DoH and DoH over Tor. And the results get more interesting as we start to kind of co-locate our services. And we notice that on an average, it improves by, on an average, it slows down by 50% and when there is service co-location, and 100% when the target and the resolvers are actually not co-located. And DNS protocols with message encryption like DNSCrypt, they tend to have much larger compute overheads and use non-encrypted channels. And these protocols have much higher response time and lie somewhere between ODoH and DoH over Tor, which is in this dotted line. So I'll keep it short for this talk, but here is a slide for your reference, which you could revisit to see the different comparisons of the various network architectural variants and where ODoH kind of fits in along with the protocol's security and privacy guarantees. And there's a link to the production service, which is the case of co-located ODoH that Cloudflare operates today. And this brings us to the crucial measurement that we're really interested in, the page load time impact. And to do this, we established a new measurement node in a lab network connected to a commercial ISP. And there is a local stub resolver, which is configured to use DoH or ODoH for different runs. And we browse a bunch of web pages, retrieve the HAR files for each one of these web pages, and then identified that using ODoH with an off-path proxy, it increases the page load time by 13% compared to baseline UDP. And using DoH with a non-co-located variant, and also the variant, and the average content page time actually changes from 1.8 seconds with UDP based DNS to 2 seconds with ODoH. And the results so far look optimistic, and we're currently looking at more telemetry to see how this looks like in clients. And in summary, like ODoH is a practical privacy enhancing protocol for DNS with a minimal page load time impact. And the performance impacts of the protocol are purely like network topology effects. So for better usage in production systems, having an ecosystem of on-path proxies and service co-location could be super helpful. All of our code and implementation is actually open source. I encourage you all to go play with it and give us feedback and see how this works. And I'd like to give a huge shout out to the authors of the original draft of the Oblivious DNS over HTTPS, Tommy and Eric, in addition to the incredible team members I've had at Cloudflare, without whose effort this work would not have been possible. Thank you. I'm open to questions.
All right, great, Sudheesh, thank you. So if you have a question, you can either raise your hand in the through Zoom, and you will be able to ask your question yourself, or you can post the question in the Q&A, and then I will read out for you. You will get a poll popping up. This is your only time where you can rate the talk. Please do so. It helps the program committee to better understand what you liked or not. With that being said, I'm going to hand it over to Ralph Weber. You should be able to unmute yourself, Ralph, to ask your question.
Yes, hello. So you've built the dream protocol of every kind of adversary that wants to exfilter data out of enterprises. Because if this get widespread deployment, I mean, there is nothing I can see that the enterprise can do to protect against exfiltration of data using DNS as an exploitation protocol, which is in use with DNS towns today. So what do you say to a CIO of an enterprise with regards to ODoH? How to protect against that?
Yeah, I think that's a great question. So there are two aspects to this that we kind of thought of, but I would be open to hearing more about it. One of it is you kind of want to protect what queries the enterprise is making on the public internet. And the other one is you also want to kind of have your own set of firewalls or like malicious website like blocking or kind of systems within the corporate intranet to kind of work correctly. There are two potential solutions, really. The first one is where you have like this gateway node, all the network traffic inside the organization itself could run using UDP-based DNS or like a DOH connection to a resolver, to some kind of a resolver or some kind of a gateway that you host inside the company, which then makes an ODoH query. So you would still in that way kind of have some control over what kind of domains people are trying to visit or what host names people are trying to visit. But I completely acknowledge and I agree that if this was just left to the user and in a corporate environment, things would be slightly more difficult. So
to protect in a corporate environment, you need to assume that your adversary has kind of connection to your network without your control. So that means it can use HTTPS to go out and ask any public ODoH server, right? So this, I mean, will not work.
I mean, it depends on how you want to, I guess, look at it internally. If all the users within the company trust the company and the resolver service that's offered there, it should be okay. And then you can protect your anonymity. Like say, for example, you're looking for a patent diagram or something like that, but you don't want to kind of leak the idea that, hey, this specific company A is looking for patent diagrams which belong to this. So yeah, I don't know if that kind of answered your question, but I would be happy to also take it, offline. Yeah.
Okay, I'll take it offline.
Yeah, there's a few other questions, so maybe if you can take it offline, that would be great. Thanks. So the poll should have come up now, so you can answer the poll. Next, we have a question from Roland Dobbins. He's asking, can you please detail the proposed DDoS defense model for ODoH, including DNS query flood against the proxy?
Yeah, I think this is a great question. This is also one of the questions that we kind of like hand waved in the paper that we wrote. We believe that the current denial of service kind of mechanisms that are in place could be used. So there could be rate limiting that is implemented at the proxies, so that the proxies are only receiving like the proxies are not undergoing this attack. But there is the potential of DDoS amplification, like request amplification attacks that happen. So that you could think of a botnet of DNS probes or like clients who are forcing a specific proxy to shoot HTTPS requests outside. So one way we kind of say this could be resolved is for the proxy to have an allow list of which domain names it's willing to speak to. Like say, for example, a proxy A is configured to speak to ODoH.Cloudflare DNS and maybe ODoH.Google DNS if Google decides to operate one, or ODoH.Next DNS or something like that. So you could do that allow list kind of an approach and then have the standard web defense, like DDoS defense mechanisms in place. And but I don't know in more detail about like the operational complexity of what this might entail.
All right, thank you, Sudheesh. There is a couple of other questions, but we are over time. So maybe Vittorio and Andrew can catch up with you on the channel, the Mattermost channel. You could discuss that. Thanks a lot for this talk. So we're going to move on with our next talk on DNS privacy, which is going to be Kazunari Fujiwara talking about how to keep your privacy with DNS over HTTPS, over CGN, CGNAT, or public NAT64. Fujiwara-san.
Hello, this is Kazunari Fujiwara from JPRS. I will talk about keep my privacy, DNS over HTTPS and over CGN, public NAT64 transition technologies, public NAT64, and open and IPv6 transition technologies and open HTTPS proxies. There are privacy issues of DNS over HTTPS DoH. DoH hides DNS query name, class, type by encryption. However, query source IP address is not protected. DoH providers can collect the whole data, query timing, query source IP address, and query name, query type, class. How can I hide my IP address from DoH providers? Previous proposals towards DNS and Oblivious DNS DoH also tried to hide query source IP addresses. However, they are complicated and requires DoH network or service providers. I like simpler solutions to hide. I'm happy if I can do it by myself. The best place to hide a leaf is in a forest. We can hide query source IP address under IP version for NAT, CGN, NAT64, IP version transition technologies, or OpenHTTPS proxies, and more. We can use different IP address direct connection to access web servers. First idea is DoH over CGN. We can hide query source IP address under low-priced mobile network. In Japan, it is easy to purchase a SIM card, 100 megabytes per month for about $2. Many MVNO operators use carrier-grade NAT for a user's network. Some of users under the same CGN may use DoH. Usage scenario is preparing DoH for the MVNO network. At least we can use different IP address for DoH and to access web servers. Next idea is DoH over NAT64. There are some public NAT64 services. They translate rewrite source IP version 6 address to shared IP version 4 address. Usage scenario is the following. Send DoH queries to IP version 4 DoH servers via NAT64. NAT64 rewrites IP version 6 DoH query source IP version 6 address to NAT64's shared IP version 4 address. It hides query source IP version 6 address from DoH servers. We need special DoH forwarder that connect to NAT64 IP version 6 address. NAT6 prefix plus DoH servers IP version 4 address, and we can use different IP addresses to access web servers. To increase anonymity, we can use multiple NAT6 services prefix and multiple DoH providers. Next slide, guys.
Fujiwara-san, this is the timekeeper. You have 5 minutes until Q&A.
Yes. Next idea is DoH over IPv6 transition technology. In many cases, multiple subscribers share one IPv6 address. And usage scenario is disable IPv6 at the client. But this idea has problems. it is weak because source IP address of DoH and WebAccess are the same. And disabling IPv6 goes against IPv6 transition. Next idea is DoH over open HTTPS proxies. HTTPS proxies cannot know the DNS query data because it is protected by DoH HTTPS. DoH provider cannot know original query source IP address. Usage scenario is the following. Send DoH queries via HTTPS proxy. Use direct HTTPS connection to access web servers. The idea requires special browsers or DoH forwarders that send DoH queries via HTTPS proxy. And this idea have a big problem. We cannot get permissions to use open proxies. And the possible solutions are DoH over Tor or providers may offer special open HTTPS proxies that can connect to public DoH servers only. And this idea is maybe similar to Oblivious DoH. And I used who am I command a query query to know my query source IP address. Dig at Akamainet servers who am I Akamainet A or query returns my IP version for IPv6 address. And I used two DoH forwarders. DoH forwarder receives queries from clients via port 53 UDP TCP and forwards queries to servers via DoH. I found one from GitHub and the other is my own. My DoH forwarder supports NAT6 translation. It receives IP version for server address and rewrites to NAT6 prefix, NAT6 address. However, it has very limited function. Next slide shows evaluation of DoH over CGN. I prepared MVNO SIM, Android phone, and DoH forwarder machine. Does the CGN hide my IP address? Dig at Akamainet server who am I Akamainet A returned MVNO's shared address. Then I can hide my IP address from DoH provider. Then I run DoH forwarder at DoH forwarder machine that uses MVNO network. Then I checked responses from DoH forwarder. Dig at DoH forwarder machine who am I Akamainet A returned Cloudflare's IP address and query time was 80 milliseconds. It is acceptable latency. Finally, I changed the PC's resolver setting to DoH forwarder. Then all queries from the PC went to DoH providers via CGN, and web access used another connectivity. Next slide shows evaluation of DoH over NAT64. I chose one NAT64 prefix. Location was Amsterdam. I agreed and followed the terms of service because it is an evaluation only. Does the NAT64 hide my IPv6 address? Dig at NAT6 prefix plus Akamainet server's IPv6 address, who am I Akamainet A returned NAT64's shared IPv6 address. Which node answered from NAT64? Dig at NAT64 plus 1111 ID server returned AMS. Query latency is 238 milliseconds from Japan. Then I checked responses from DoH forwarder. Then I started special DoH forwarder. It received local queries via DNS over port 53 and forwards queries to DoH server's IP version address via NAT64. Then I checked responses from DoH forwarder. Dig at DoH forwarder ID server returned AMS, and dig at DoH forwarder DNS-OARC network returned OARC's IPv6 address, and however, latency is about 1 second from Japan. These are limitations of DoH over CGN NAT64. DoH over CGN NAT64 open proxies nullify the traffic control of CDNs. DoH providers can track by using TLS session information. My DNS forwarders close TCP/TL session on every query. Public NAT64 services are located in Europe only. High latency 1 second from Japan because UDP RTT is 238 milliseconds. Conclusions. Though providers can know both query source IP addresses and DNS queries, these are the sensitive dataset for privacy. To protect our privacy, we can hide our source IP address by existing tools. Though over CDN with low-priced MNO SIM is feasible. Though over NAT64 is feasible in European region. Though over open HTTPS proxies or Tor may be feasible, but not listed. That's all. Any questions and suggestions?
Thank you, Fujiwara-san. We got some time for questions. So please, if you have any question, either write them in the Q&A tab or raise your hand to ask the question yourself. You're also going to see the poll popping up, and that's the only time to be able to rate the talks. And that being said, if anybody has a question, please raise your hand or write it down. In the meantime, I may have a question. How do you think how feasible this could be done? So I think I like the approach, but aside from maybe the DOR over HTTPS proxy or Tor, the other one seems to be a bit harder to do. Like you will need to carry a phone essentially with you to be able to do that. What do you think about that?
Oblivious DOR may be similar to DOR over not open HTTPS proxies. And if some providers may offer special open HTTPS proxies, I think.
Yeah, so it's, I think the over NAT64 or over CGNAT may be a bit harder to do. I mean, somebody will need to have physical hardware with them to carry around. I think that's my point. Do we have a question here in the Q&A? So let me, Andrew Campling asked, or rather said, Alec Moffett gave a presentation on DOH over Tor. He's providing the links. I'm not going to read the link here. You may find it useful to compare your results with his.
Yeah.
So if you look at the Q&A tab, then you will be able to get the link from Andrew. Or maybe Andrew, you can post it in the workshop Mattermost.
Thank you.
All right. So I guess if we don't have any other questions, let's move on to with our next talk. Thanks a lot, Fujiwara-san. Now we're going to go to Giovane Moura, who is going to tell us about the public disclosure of a DNS vulnerability. Giovane.
Thanks. Yeah, good morning, evening, or afternoon, depending on where you are. Yeah, thanks, everybody. So yeah, today we're gonna publicly disclose a vulnerability that we came across last year, and this is actually a follow-up that of some of the responsible disclosure we've been doing. So this work, I'm Giovane. I work for SIDN Labs. But this work has been done together with Sebastian, that works for Internet NZ, and John and Wes at USC, ISI, University of Southern California. And before we get here to this day today, we actually were very careful to be sure we follow responsible disclosure practices. So before I dive into the details, I think a lot of people already know about this here because the first time we talked that publicly, but in a private session for members only, was during OARC 34, actually 3 months ago. And after that, we presented the other venues, as you can see here in this table. And today we make it publicly 90 days after. But even before the private disclosure we did it at OARC, we had already been in touch with some vendors, some DNS vendors and operators. So we feel that we have given everybody else that we could reach enough time to address the issue, this vulnerability. And just a quick update, since the notification, we are very happy that Google and Cisco Public DNS, the OpenDNS, fixed their software in regards to this vulnerability. The first time we analyzed TsuNAME, there was an event that happened in New Zealand. Most queries came from Google, and we later measured that, and after the fix, and Google really does not actually flood servers anymore when they follow these conditions. We also released a tool called Trufflehunter that allows authoritative server operators to identify records in their zones that are actually vulnerable that have a misconfiguration that trigger the sort of attacks, which is called cyclic dependencies. And once we released that, there was a great response from the community. And I mentioned just a few of the folks here because they pretty much rewrote a lot of the code. Shane made it like very hyperformatic. He made it synchronous. There are all the users there, but I don't know their names. I know probably who they are, but they have cryptic usernames on GitHub, so you can click here and check who they are. But I'm pretty happy with the community response. We're very thankful to everybody that in OARC and DNS in general that contributed to that. And now we know far more about the problem, and we're releasing together with this presentation a security advisory, which is a document intended for DNS developers and operators and authoritative server operators and DevOps in general. There are some tests there you can do in your software to see if it's vulnerable or not. And if you're interested in more details, we are also releasing a technical report. You can go to TsuNAME.io. It's on the homepage there too. So just a quick recap. It's a TsuNAME vulnerability. It's a vulnerability that can be used to deny servers authoritative servers. It requires cycle-dependent NS records. Requires vulnerable resolvers, and vulnerable in this case means that the resolver, once it finds a cycle-dependent domain delegation, it would start looping, sending queries nonstop. And you need some user queries to trigger that resolver. And we actually were able to go from 10 queries per second to 5,600 in our experiments. So it's also in a technical report. And if you want to mitigate it, if you're running your own zones, please make sure you don't have cycle-dependent records. This is particularly important for if you're ccTLD, which has open registrations, because, well, you know, registrants can change that at their will. So be sure you make sure that you don't have those in your zone. And you have to actually, it's not only Trufflehunter is documented there on GitHub, does active measurements, because you need to get information outside of your zone in the process too. But anyway, so run it. And if your resolver dev operator, if your resolver is not capable to detect the start of cycles and gets into loop, you should fix your code. But to what we found, open source projects that we analyzed, out of them they are able to detect, and they're not vulnerable to TsuNAME. And so we call it TsuNAME. That's the official website. It's a classic tsunami painting from Japan. And so just recap, cyclic dependencies were first described in 2009. The simplest example is when you have two domains, at cat.nl, which has as an NS record dog.nz. But if you look at dog.nz later, it points to cat.nl. So it means like you keep on going from one zone to another, you're never able to retrieve a record. And we found that in the wild in New Zealand, it happened in 2020. Two domains were misconfigured, 50% more traffic. Mostly were A and quad A queries for these IP addresses that cannot be retrieved, and mostly were for Google Public DNS. Luckily, that has been fixed.
Giovane, here's the timekeeper. You have 5 minutes until Q&A.
Thanks, Manu. So as I said, traffic surged 50%. The blue line here is the total aggregated traffic for New Zealand, and you see that goes up where there's a cyclic dependency here. Most were from Google, as I said, but the bottom line here was just other autonomous systems were also sending a lot of queries. And a threat profile, an attacker could hold multiple domains and intentionally create cycles and inject queries using a botnet, and that can be easily weaponized to DDoS authoritative servers. This was not an isolated event. We have been able to reproduce that multiple times. That is also a technical report. We configure, for example, 10,000 RIPE Atlas probes to set one query per resolver. And what we found is that they, after they set this query, which is this point here, this green area here, some resolvers would be in loop. As you can see here, they keep on sending queries like forever. And if you send recurrent queries, it gets even worse. But well, to prevent this, you have to fix the resolvers. Google and OpenDNS already did it. Run Cyclehunter if you're an authoritative server operator. And this is the tool. Cyclehunter, if you're interested, is a tool that reads its own files and tries to resolve every single NS record on the list. And if those that fail, that timeout or has some sort of error, mostly timeouts, it will try to identify on the parent zones that they're actually cyclic dependent. We found, look into the wild, and when we looked back in 2020, there were not many of those in the wild, but that could change. And for example, .com had 21 cyclic NS records only, affecting 1,200 domain names that use those NS records, but that could change. We have, as I said, we evaluate resolvers. Most of them don't have any issues, the latest versions, but some old versions have. We confirmed Windows 2008 R2 and an old version of PowerDNS 2. So what you have learned since the private disclosure? I think somebody asked me, what do you, if you do longer cycles? And I remember running that, and I thought, I remember the results that, well, the short stories that makes the problem even worse. So the green area here is when you send queries with RIPE Atlas to clients to resolvers. But after that, the resolvers have no more user queries, but you still keep on looping. And bear in mind that this is after Google fixing public DNS. So you can even have longer, triple, probably quadruple cycles of cyclic dependency, and it gets the problem even worse. I think it was Roy Arendt who asked me about CNAME cycles, and I ran experiments with CNAME. They're not that problematic. CNAME cycles are well known and they've been documented since RFC 1034. So luckily, it's not a big problem. If you have a cycle of CNAMEs, that's all right. You can see here that doesn't cause a big issue. I'm very thankful to this anonymous EU-based CCTLD operator who reached out later after the presentation at the OARC 34 and shared with us this beautiful graph, but terrible to experience, that they also had their own TsuNAME related event before we privately disclosed. And they had 2 domains in their own zone that also were configured as misconfigured cyclic dependencies, and their overall traffic grew by 10 times. So we're not the only ones experiencing that and seeing that in the wild. So if you look back, it's kind of a wave, but in reverse shape. We also identified the root causes of looping. Some resolvers would just loop if they find the cyclic dependent NS records, and some resolvers won't loop, but they want cache. So every query of a new client for the same thing, you're going to trigger a new set of queries. And if you want to fix it, detect the loop and cache it. That's the solution for resolver developers. We confirmed that Google fixed public DNS, as I said. This was Google before fixing it. We get a lot of queries from Google in one particular experiment. We repeat the experiment, and you see that Google now sends very few queries compared to that. So kudos to them too. I think these questions were presented in the last presentation, so I'm gonna, I think, stop here because of time. You can read them later. It's just like if you want to strike a wonder, if you want to be, if you're safe or not. And I think that's it, right, Daniel? I guess. And for, just to summarize, if you're an authoritative server operator, check yours on. Use Cyclehunter. It's being developed by a lot of people in the community, so thanks to all of them. And if you're a resolver operator, DevOps, detect these dependencies, return serve fail, and cache serve fail. The slides and reports are at TsuNAME.io. I want to explicitly thank all the folks at the OARC, Keith, Dinesh, for all your support and helping us here just publicly disclose that and privately as well. And now the work and entire OARC community got engaged into that, and the developers that contributed to GitHub. So thanks everybody for that. And I think that's it.
All right, thanks, Giovanni. It was very nice to see the after the second part of the talk after some months waiting for this to come up. Right, so yeah, we got time for Q&A. We got about 5 minutes. So again, if you want to ask a question, please either raise your hand in the Q&A tab, or, well, sorry, raise your hand or write your question in the Q&A tab. Again, you're going to have a poll which is going to pop up. This is that just popped up now. This is your only time to rate the talk. Please do so. This is very helpful for the program committee. All right. In the meantime, so I mean, I'm hoping we don't have these kind of issues popping up too often. But I guess from your learnings going through this vulnerability, what will you do differently the next time? Like, what would you suggest the community to do when a vulnerability is found? How could we engage faster, maybe with operators or whatnot?
Yeah, so this is, for me, was the first time I'm doing actually public disclosure in private. So I had no experience of that. And I got to tell you, I mean, I'm very happy with the community response. I cannot be more happier than that. I think OARC was a great venue because everybody got together, and having a platform as Mattermost that helped a lot too. So I think we did good as a community. And if you can look at GitHub as well, a lot of people really contributed a lot to the code. So I'm actually very happy. And I had a lot of discussions in parallel, also in Mattermost. For example, I talked to Benno and Elnet Labs, and they do Unbound, a resolver. And he was pointing that cycles is something they're always looking out for when they're doing the resolver development. And if you look at the changelog of Unbound, if you look just for cyclically or cycle in the changelog, you're going to see a lot of entries where they found some instances that could happen and they fix it. So this is an instance of those kind of problems. So it's for a resolver developer, they're very concerned about that. So I think that overall approach, I think went very well. I'm very happy, especially with Google fixing it in public DNS, because I know for another CCTLDs, I know at least of 4 who experienced these events, and was mostly from Google. So they were terrified to actually having the biggest resolver on the internet pointing at them, and this is now fixed. So I think it's been great, a great contribution, and engagement from the community.
And this is, I think, this is a good lead for Dave Feldman question. Your paper says that authoritative servers are the target. Do I understand correctly that as vulnerable resolvers are fixed, the danger to authoritative servers diminishes? Now that Google and OpenDNS have been fixed, what's the assessment of a real danger in the wild?
So they have been fixed, but I can give an example here. This graph here, this was produced after Google and OpenDNS being fixed, and you see there's a lot of these are resolvers in loop sending those queries, and there are still, you know, it does not only coming from Google. We found many other autonomous systems that actually have the same problem, and I think it's a classic problem of software update. There's a very long tail of software that never gets updated, and these are the problematic ones. It's not only we here or Google fixing, but it's like some small resolver somewhere that was left on a corner and it's been doing that forever. Nobody wants to touch it. These are the kind of problematic resolvers that could be, you know, if you have a large botnet, probably can trigger those to, you know, send tons of queries. So it's a classic problem of software update when there's a vulnerability. It's very hard to actually handle the long tail. But yeah, in general, I'm very happy that Google and OpenDNS, I'm very happy that they fix it, but we never fully evaluate the entire protection of this. You know, if someone would use a botnet, we don't know what could happen, but yeah, we have to public disclose that and hope that people update, but at least the newest versions of the resolver software is already fixed.
All right, thank you. The next question is from Roland Dobbins. Can you please discuss on-network DDoS mitigation tactics? For example, detection and suppression of repetitive query sources or sources.
So in regards to TsuNAME, let's see if I think I have these slides here. Let me see if we can get a record here. So what you're gonna see in a TsuNAME related event is, for example, the authoritative servers of dog.nz. In this case, let's say this is the zone you're analyzing, dog.nz and cat.nl, and they are cyclically dependent. What if you run cat.nl, if you run actually .nl, what you're gonna see is a lot of queries that come to you trying to get this A record here. So you're gonna see like, it's on a technical report. You can see like, we describe exactly kind of queries, and they're very repetitive. They're unique. They are all the same. So if you're going to filter based on a QNAME, that's very easy to filter. But the problem is you may get a lot of people asking the same thing. But if you filter on QNAME, it's pretty straightforward.
Okay, cool. Okay, we slightly passed the Q&A. There is no more question. There is a comment from Jake Zach, which I'm going to read. We saw this from time to time on Cirrus TLD's infrastructure. The UDP packets were many, but it was rate limited, forcing these repeated queries to TCP that really caused resource issues. The situation was unideal, but it was a good exercise in problem solving, and it's great that you brought the community together to address this. All right.
Thanks.
With that being
Jake,
said,
for your support and your help as well too. Yeah, I mean, as he's saying, like, if you try to not respond, the resolver is going to try TCP, and then you're gonna, your fire now has to deal with a lot of stateful queries, repetitive queries. Well, good luck with that. Kind of
well, I guess that I understand that is basically what happened. All these queries were retried over TCP because they were legitimate queries. Yeah. All right, we're running slightly out of time. It's time for a quick break. So we will restart at 5:40 UTC sharp. You folks can go and chat face-to-face on the spatial chat. Please, you will see the details on the rolling slide. Please do not share the link. I would like again to thank our workshop sponsors, Farsight and VeriSign. And with that being said, enjoy your break, and I'll see you in a few minutes. Hey, welcome back, everybody. I'm now joined by Ewan from VNNIC, which is going to be our timekeeper. And without further ado, I would like to introduce our next speaker, Liman, who is going to talk about 30 years of operating a root name server, the challenges now and then. Liman, on to you.
Yep, thank you. And thank you all for attending, and good local time to you, wherever you are. My name is Lars-Johan Liman. I work for NetNode, and we operate one of the root name servers. I thought it might be a good idea to give a little presentation of the historic view of this, since we're actually celebrating 30 years this summer. So a long journey began on July 28th in 1991, when the following two records were entered into the root zone, officially starting the operation of the root name server operated from Sweden. At the time, it was under a different name because the names of the root name servers were changed later on, as we will see. So this summer, that will be 30 years ago, actually for us both, because the 30 years is not the scary number. The scary number is that I've been along for 29.5 of those years. And that's actually a frightening number when you realize it. So what was it like back in 1991? Well, a note singular root name server in Europe at the time, it was just a simple workstation on a desk in an empty office. At the time, it was operated at the Royal Institute of Technology. That's the technical university in Stockholm, and that's the nursery of internet in Sweden, if you wish. It wasn't where the first experiments were run, but that's where it was started to be operated on a scale. And the KTH NOC, the KTH Network Operation Center, was the cradle for SUNET, the Swedish University Network, which was the first internet service provider in Sweden. So in July 1991, this was just a simple Sun 350 workstation with a Motorola 6820 processor and just 4 megabytes of RAM. Now, you have to realize that 30 years ago, the internet was something completely different than what we have today, and the web wasn't even invented, so it was peaceful and quiet on the network. You could count the emails and you could see the files as they were being transferred with FTP, and that was about it. Oh, there was the odd login using Telnet as well. Now, that Sun 350 was actually just a temporary machine because the one that was on order that we waited for hadn't been delivered yet. So quite shortly after July, and I don't know the exact date, it was replaced by the real server, which was the Sun 465 or SparkStation 1 Plus. But again, still a workstation. And that's the machine that was in operation when I started to work for the NOC back in February of 1992. We were already up to 40 megabytes of RAM. still just 10 megabit Ethernet connections and so on. And at NetNode, we actually have a museum. We have tried to preserve hardware from various stages of our operation. And true to that, we actually have the actual machine that operated in 1992 when I started to work for the KTH Knox. The lower one here it's marked tftp.ebound.net because when it was retired as a root name server, it was repurposed to be used as a TFTP server for ebound, a pan-European operator at the time. But the machine is the actual physical machine that operated. And on top of that, you see the next generation that followed on that from 1994. Which was the Spark Station 10, then much bigger and much more powerful. Now, what were the challenges back in 1992? Well, you wouldn't believe this, but getting the zone files into the root name server was actually a challenge. In the day, Sweden was behind, or actually, I think the entire Nordic region, because most of the traffic from Nordgenet went through Stockholm, sat behind two 4 megabit links to the United States. And as you can imagine, packet loss was actually a severe problem. 30% packet loss was not unusual, and I remember seeing more than 50% packet loss. You don't have a very good experience when you have those types of packet losses. So DNS zone transfers simply didn't work. The DNS software would time out when the zone wasn't propagated properly. So we had to use FTP. FTP was somewhat more resilient to packet loss, and this was actually a manual endeavor. 2 or 3 times per week, I would sit down and I would log into the server in the US, and I would copy the zone files using FTP, and then I would manually diff the zone files to the old ones to see what changes had happened and if there were any errors. Occasionally there were. I remember one time when an entire nation, a CCTLD, was inadvertently dropped from the root zone file. So that entire country risked dropping off the internet. But fortunately, we caught it before we reloaded the server. So that never happened. Another challenge we had was zone content mix, because the server at the time operated both as a caching resolver and as an authoritative server. We know nowadays that that's not really a good idea, and it was even a worse idea at the time because zone boundaries were not enforced in zone transfers. So you could put any data in any zone file, and if you were unlucky, they would just show up in your server. Zone transfers were honestly less of a problem, but when you loaded the zone file, if someone put in a totally different record in there, it would just be loaded. It also served several levels of the root, of the DNS tree. Com, net, and org and .se were also in the same server. The server would just hand out any records that happen to be match the query, and that can be good and bad, and there are some bad consequences of that. We've learned a lot since then. Software has improved tremendously since then, so these are no longer the same challenges as it once were. And the human errors that we still see don't have the same impact as they had back in the day. I've been chasing broken A records from Switzerland to northern Sweden. Took 6 months to clear the DNS of a broken A record that hampered the service of the .se domain back in, 1995. In the mid-1990s, we started to see politics popping up. The internet picked up speed, and when it picked up speed and attracted more people, business also increased. So money started to be an issue, and that attracts politicians. One issue was acceptable use policies. Some, specifically academic networks, had limitations on who got to use the network, and that created the notion that possibly traffic to the root name servers, remember only 9 at a time, was being filtered because of these acceptable use policies. That was never the case with the one in Sweden, but there were allegations of that. So we needed more root name servers. The distribution of the existing 9 was an issue. Only one of them was placed outside the United States, and we needed more. So in 1995, the root servers were renamed. We didn't have any extended DNS at the time, so there was a 512 byte limit on the UDP packets, and the priming query that the server asks in the beginning to figure out the list of the root name servers limited the set of servers to 9 because we couldn't fit anymore in that 512 byte packet. This clever new scheme took advantage of the DNS message compression, and we suddenly, by just changing the names of the servers, we had room for 4 more. So that's when the letters were introduced. So A through I were already operating, and we now added J, K, L, and M. As we got near the turn of the century, the internet had grown to a size where it wasn't really feasible to have one single person at the IANA be in charge of the root name service system and the entire root zone and its administration. So as an international effort, ICANN was created, and John Postel, who was the head at the IANA at the time, and also who was in charge of the root zone, was very much in this process. He was one of the driving forces to create what's now ICANN and an international community around that. But he died. Suddenly in 1998, John Postel passed away, and this was actually the first time when all the root server operators sat together in a meeting. It was a fairly covert meeting because we didn't know anything about what the attention would be. So we sat down and talked to each other and realized that we need to coordinate, we need to keep this running, and we also all agreed that IANA is the source of data and no one else. And that's a statement that holds true today still. ICANN was created. The Root Server System Advisory Committee of ICANN was one of the initial advisory committees. So it's actually an integral part of ICANN, and it's still operating today. Another thing that happened around the turn of the century was the year 2000 bug. That was a lot of brouhaha around that, and we had our fair share of attention around that. So we did test runs, we changed the clocks of the servers, we did a lot of things just to make sure that everything would run smoothly. But regardless of that, we actually had staff on site at the university during the night. There were a couple of guys who volunteered to take the offer of a fat bonus to their salary to spend the night in the computer center. But everything ran just smoothly on our side and all the root name servers, so that wasn't an issue for us at all. So what do we see? Which challenges do we have nowadays? Well, the internet and the root service has gradually turned into an infrastructure, and my own definition of infrastructure is that's something that you don't realize is there, and you use it all the time every day, and you don't realize that it's there until it's missing. You drive on the road and you don't really think about that there's a road there until it's missing. You turn on the tap to have some water and you don't really think about it until it's missing. And the same goes for the internet now. If the internet stops working, you realize it, but you use it all the time, and now it's infrastructure. So we have much higher demands on service stability, and actually things that you might not think about, but policy stability and financial stability as well for the root service. So how does NetNode try to meet these challenges? Well, on the service side, we work a lot with provisioning. As you know, we operate on Anycast network for our service. We have dual systems for all critical parts in the provisioning chain. We use VPN-based transport to make sure that everything is, the integrity of all the management is okay. And we use machine-generated configurations because we want to limit the amount of errors introduced by humans. We collect statistics. There is an RSAC document, number 2, that specifies the statistics that we're supposed to collect on behalf of the public, but we collect a lot more. We use that to monitor the health of the system. There was a root zone scalability study back in 2009, which looked at the scaling issues of the root zone. That was in conjunction with the plans to open up for new GTLDs. We required that there be a study done so that we would have some understanding of how quickly could we add new GTLDs to the root zone. That was, so to speak, an initial work, and after the transition of the IANA function back in 2016-17, the root zone evolution review committee was established, which now keeps an eye on things like that. More reachability to our service is another very important issue. As I said, we use Anycast. We have maintained 70 sites, or more than 70 sites. We have thousands and thousands of peering relationships. We use route servers extensively where we can, where we're connected. We use PeeringDB to find new peers and make sure that we have the right relationships. We maintain dialogues with our site hosts where we are located with our servers. We sign our routes with the RPKI, so that those who receive our routes can validate that they're correct. And in all this, we actually are able to draw from experience of operating internet exchange points. NetNode has a couple of business legs, and DNS is only one of them. Another one is operating internet exchanges. That means that we have network and routing expertise in-house that we can draw from when we work with these things.
Sorry to interrupt, but you have 5 minutes remaining until the Q&A.
Yeah, thank you. Policy stability is another thing. Global DNS policy affects the root service more than other services, because the root is at the pinnacle of it. If you do something that influences the root, you will have an effect on the entire DNS tree. So there are lots of places where policy that touches on DNS service, and especially the root, is being discussed and maintained. We have, of course, the IANA, which is operated by the PTI and which is, so to speak, monitored by the Customer Standing Committee. That's one place where DNS administration for the root zone is handled. We have the root server system advisory committee in ICANN that deals with policy in relationship with ICANN, the other ICANN constituencies. RSOARC, I've already mentioned. There's the security and stability advisory committee, and now the root service system governance working group, and that's all within ICANN. The governance working group is an ongoing working group right now that is looking to modify and improve the accountability framework around the root server system. It's been very unclear for the past 20 years how the accountability works, and we want to make that better and improve it. Then there are a whole slew of other places, the ITU, the European Union, the IETF for standards, RIPE and its DNS working group, Center, which coordinates top-level domains. All these places discuss and relate to the root service. So in order to provide a good service and be in touch with everyone who feels that they're in contact with the root service, we have to be everywhere, and we really try to be there. So we attend all these places and conferences, and we are also happy to talk to you in all cases. If you can't find us out there, do reach out to us if you have any problems or any issues that you would like to discuss, or just support us. Financial stability is another interesting issue for root servers. Operating a root server requires neutrality and independence. We are there to serve the entire internet, not just a subsection of it from any aspect. This is actually even documented now in an ARSEC document with the number 42. That is an interesting statement. You should take it with the next bullet here, which is that there is no a priori source of income. The root server operators are not paid for the service by any specific source that relates to the root service. So every root server operator has to fend for itself and find some way of supporting this service financially. Now that varies a lot between the various root server operators, and that's a good thing. The motto between the root server operators is diversity is good. And the NetNode way is that we provide commercial DNS service from the same platform to other players, primarily top-level domains. And from that, we earn some money that we can use to pay for the root service. And this multitude of customers actually is a good thing, because that helps us to avoid the problem that you may have if you have a single source of money, which is that single source actually can probably influence you more and in an inappropriate fashion. But when you have many customers, a single customer doesn't have that power. Deployment challenges. Well, finding the right place, the right people, and stable host. You can find perfect people to work with, and then 2 years later they leave and move on, and suddenly you don't have a good contact anymore. Logistics is a nightmare. Shipping servers across the globe to dark corners that you've never heard of. Well, don't go there. And always to make the service cheaper, because the cheaper we make it, the more sites we can deploy, and that's always a goal for us. The more sites we can deploy, the better the service will be for the end user. Zone propagation in a timely and synchronized fashion is always a problem. It runs fairly smoothly these days, but we need to keep a close eye on it. So monitoring, statistics collecting, all of that is done constantly, and is a challenge that we need to address, because the administration links we have to these sites are not always 100 megabits links. And of course we have the political changes. The big challenge is to ensure that all decisions that may impact the operations of the root service everywhere on the globe are based on facts and not on misconceptions. There are so many misconceptions about the root service system out there that you couldn't believe it. And we try to provide a clear picture of how it works, and to make it clear that its purpose is technical infrastructure and nothing else. Thankfully, we are not alone in that endeavor. Many people do the same, and we are very thankful to them. That's where I intend to stop, and I will be happy to take any questions.
Thanks a lot, Liman, for getting us through the history of the root name servers. I'm very glad that people are not making diff manually to manage the root. All right.
I stopped long ago. Yes.
we got a few questions. Ralph has his hand raised. Quickly before Ralph, before you talk, if you have any questions, please ask them in the Q&A tab or raise your hand. And also the poll is going to be popping up soon, so you can provide feedback. Thank you. Ralph, go ahead. You can unmute yourself.
Yeah, hello. Thanks a lot, Liam. That was a fantastic talk. One question I have is, we've seen over the last sort of 30 years, root service becoming more and more important, traffic getting more and more. What do you see sort of, maybe not 30, but say 10 years down the road with RFC 7706 and other technologies? Where will the root service be in 10 years?
Can you please remind me of 7706? What's that?
Running a local route, pretty much.
Oh, okay, thanks. Yes, you are right. I think this is going to change over time. Running local routes is one thing that is going to change this, and I think that is to a largest extent a good thing, except it does change debugging somewhat. It's always, the more players you have involved, the more difficult it may be to debug systems. In addition, I believe that the DOH and DOT are going to change the overall picture a lot. So to be honest, I think that the relevance of root servers is slowly declining. And I think it's healthy for the internet to not depend on single points. The more we can spread things over the network, the better. But I think it's going to be a very gradual and slow process, and that's also a good thing because we don't want to make any sudden changes to these important infrastructure systems. Slow is good.
Does that answer your question, Ralph?
Yeah, absolutely.
Okay, perfect. Thanks. We got actually, I guess, a follow-up, well, a question at least that nicely follow up from Sebastian Castro on the Q&A tab. He's asking, what do you think will be a future challenge for root servers operator? Scale, financial, pressure to open operations to anyone?
Interesting question. Thank you. The scale is one factor, but again, if you balance that to Ralph's comment with local operation, I think that's going to balance itself. So that's not a huge issue, I think, and also we can probably come up with ways to make the service cheaper, which means that we who actually operate root servers can deploy in more places for the same amount of money. Financial, maybe not. It depends on the relevance of domain names, actually, because as long as domain names remain relevant and there is a financial turnover in the domain name business, we can probably find ways to finance the root service, because the top level domains are utterly dependent on the root service. So there are we can probably find ways where money can be funneled to the right places. Also, in addition to that, this root server system governance working group that I mentioned is working on the accountability framework, but also is looking into the financial situation of the root server operators. So that is being looked at. We are very far from landing at a certain viewpoint there, but the issue is on the table at least. So I think whatever happens is going to happen slowly so that we can adapt systems. And I don't only mean the DNS operations systems, but also the financial systems and the policy systems around this gradually as we move along. And I think we are in a good place. We are doing the right things. We are looking at the future. So I'm not really worried. There will be changes, but I don't see them as extremely challenging, at least at this time. Thanks.
Thanks a lot, Liman. That was very interesting talk. I think I'd like to chat much more about this kind of history. All right, without further ado, we're going to move on to our next talk by Ulrich Wisser. He's going to tell us about multi-signer DNSSEC automation.
So, multi-signer DNSSEC automation. Yes, so my name is Ulrich Wisser. I work for the Swedish Internet Foundation, and this work is done together with Steve Crocker, Schumann Hook, Eric Osterweil, and a few other people. And well, let's dive into it. No. So yes, so multi-signer DNSSEC model. There's actually an RFC that Schumann has written, and it specifies that how you would run a DNSSEC sign zone with two independent DNS providers. And it comes from a problem that Schumann had in his work at Salesforce, where they actually wanted to use two large-scale DNS providers. And so there's a few procedures you have to follow to do this. And the the actual providers need to give you an API so that you can do the required operations. And so when I first read this draft, and I have said this in other places, I thought, okay, who in the world is going to run a DNSSEC signed domain with 2 independent providers? This needs to be a like special super case that is, 5 people in the world will do this. But you all know how this goes with these predictions about 5 people in the world in IT. Yeah, so turns out if you have a DNSSEC signed zone and you want to change your DNS operator, and without going insecure, what you have to do is basically join them in a multi-signer setup, and then the old provider leaving the multi-signer setup. And that's how you transfer a domain between 2 providers. So this multi-signer has suddenly a really huge use case, because I mean, moving a domain from one DNS provider to another is a day-to-day operation. And so what is it what you actually have to do? Now in the, let's say, simple idea would be you have these 2 providers, provider A, provider B, they sign with their own KSK and ZSKs, and you would have a DS record in the parent that points to these 2 KSKs. And there's one problem here on the, let's see if this works, here on the provider A side, all the data is signed with the blue ZSK. And on the provider B side, all the data is signed with the red ZSK. So if now you asked, let's say you ask provider A for the key set, you get these 2 keys, and then you ask provider B for data, you get data that is signed with the red key, but the key set that you have at hand has only blue keys. And that's not going to work. So you cannot validate. And of course, it works vice versa evenly. So this setup is obviously not working. And so what you have to do is you have to copy the public part, the DNS key record from your zone from provider A to provider B, the ZSK from provider B to provider A, and then you do the parent thing and point out these 2 DS records to the 2 providers. And now, if you do the same thing again, you get the key set from provider A, and data from provider B that is signed with the red ZSK. Well, you have the red ZSK, and so you can validate the data. Well, that's doesn't sound so complex. We have to think a little bit about it, but it's not that complex. But still, there's all these steps involved that you have to do. There's a lot of TTLs you have to watch and things. And so this is, I would say, a typical example of something that should be automated. And that is what we're aiming for in this project. So in the RFC 8901, it describes how a typical setup for multi-signer could look, but it doesn't describe all the algorithms you would have to follow, how you start this, how you add providers or detach providers, and all this stuff. And so we're aiming to do this, to make it more practical application, even aiming to writing a software that can do that. And so we're trying to write a new draft. We are in the process of doing it, and it will, specify all this, the algorithms for doing this. And the draft makes heavy usage of CDS, CDNS key, and CSync, and that is like the basic building block of automating all of this. And so the operator handoff is basically a special case of the multi-signer, where you say that usually today, if you change operators, you go insecure because the process is so complex that nobody will do it. And for a single customer, a DNS operator, that would be really, it's a manual procedure that costs a lot of money, so you don't do this. But it's a really bad choice for people. I mean, there's a lot of organizations out there that for compliance reasons maybe can't go insecure. There's a lot of organizations that of security reasons don't want to go insecure. I mean, we all remember the MyEther wallet incident, and I mean, nobody of us wants to go MyEther wallet to go insecure again, right? So what are these organizations supposed to do? And so there need to be a way to do this, and there need to be a way to do this, you know, in very ordered and safe for everybody. And so the operator handoff is the special case for the multi-signer.
So timekeeper, sorry to interrupt, but it's 3 minutes until the Q&A.
Yes, I speed up a little bit. So we have we use CDNS key records, and that is of course to update the DS records in the parent. And there is an RFC for this. Actually, there's 2 that you need to follow. And yeah, and then we use the CSync record, which does the same thing basically as the CDNS key record, but for other record types. So, and we are going to use it for the NS set to update the NS set in the parent and the glue records. And so we're going to do if you want to bootstrap a multi-signer setup, it's basically that you have a DNSSEC signed domain on one provider. And you can do this even with CDNS key that is specified in the RFC. And then be automating the rest of the steps. I go through this quite fast now, but we're not talking about how you would synchronize zone data. That is out of scope for our work. That you have to do some other way. So what you have to do is you exchange the ZSKs, you wait TTL, then you set up the CDNS key RR set. And if you look at this, in the first step, if you exchange only ZSKs, you will have different DNS key RR sets on different name servers. So the names is, but for CDNS key to work, it needs to be the same RR set on all of your servers. So this has to be synchronized over all servers. And when you publish it, you have to first wait that the parent updates, and then you can remove the CDNS key set. That is optional, but recommended, I would say. And you wait again for the DS DTL, and then you can exchange the NS sets. And here you actually want to synchronize the NS sets. It's not 100% requirement, but I would say it makes life much easier for you. And then you can make or you need it. Yes, you need a synchronized NS set for the CSync record, because otherwise the CSync record will not work. And then you go to the parent updates the NS set, and you have a working multi-signer setup. And yes, I think for brevity, we hop over the detaching. So what we have left to do in our work is we have not yet specified how to roll keys. And I would say the key rollover is something that we can, it's a straightforward work, I would say. It's not that hard to specify. But then the last 2 points here, algorithm rollover, that is a tough problem. And the last one, signers with different algorithms, is actually something that would need to be some amendment to the DNSSEC protocol. And with that, I would like to say thank you for listening. Please find our project on GitHub and review the draft.
All right, thanks, Ulrich. We have a bit of time for Q&A, so please, if you have some questions, ask in the Q&A or raise your hand. And that being said, you should also get the poll coming up soon that you can use to rate the talk. So I guess I'm going to throw one question quickly. You said you have made a proposal. Do you have a draft already? Did I miss something, or do you have a draft
yes.
already?
This is a link to a GitHub organization, and then we have a repository that with a draft.
Oh, so within the org, then there is a draft.
Yes, and of course it's we started a draft, so it's not ready yet, but we're working on it. So when we would participation is welcome.
There is no version 0.0 yet.
Yeah, we submitted a version 0.0, but I would say it needs a lot of work before you before the DNS working group would be willing to adopt it.
Cool. All right, then I don't see any questions yet. So I guess we are going to move on with our next speaker. Ulrich, thank you. Can you please unshare your video? And so next we're going to have Kier, who is going to tell us about DNS migration, getting it done. I can see your screen, your slide full screen.
Hey, so I'm Kier, and I'm going to talk today about DNS migrations and just looking at a process which I think gives you a reasonable chance of success. May not be the most cutting edge or exciting topic you'll hear throughout this workshop, but I think it is practical. And certainly over the last 15 years or so, DNS migrations have consumed a reasonable amount of my time and continue to do so. So it's definitely a thing. Okay, so briefly, but no less important, we're just going to do a little bit of upfront analysis before we get ready for the migration. So look at the data, if there is data that we're migrating, understand the state of that, look at all the systems and platforms that integrate and interact with the target platform and check that, one, they can get to it, and two, once they're there, they can do what they need to do with it. And then look at how clients are consuming that service and give them the optimal responses and resolution. Also consider complexities. Now, I have put DNSSEC here as a complexity, and I will admit that I've never actually done a DNSSEC migration in production. So I would assume that would add some level of additional requirements to look at, but it would be useful to hear from someone who has done one. And then I think the key part of this process is really to create a migration strategy and run it through in the lab. And so I've got 3 key steps here, which is test, test, test. And actually, I quite like the analogy of the eye test image we see here. So, you're there, you're staring at some letters on the wall, and you're basically getting your prescription fine-tuned until you have the best eyesight ever. And that's really what we're trying to do in this test phase for the migration, is to fine-tune the migration process, run it through a few times, and then get a migration plan together where we have detailed actions, so we know every activity that's going on, what platform it's being done on, what the execution task is, who's doing it, what time it's being done, and how long it's going to take. And then once we have fine-tuned our migration plan, we are ready to crack on and start to execute the actual migration. So if we're talking about data, stages for this process, we will export data from the source platform. And how do we get that data? Grab the zone files, do zone transfers, bulk export from command line. And then look at the data and understand if it needs to be transformed. So can we just run it straight in from the old system into the new one? Or is there a need to change the format or the structure of the data? Or does it make sense to, is there an optimal way that we need to present the data when we're importing it? Typically don't have to start from scratch, and normally there's some vendor tools which will help to create the data into the right structure. Or I've seen a script online where we'll do a zone transfer and we'll create an XML file which you can then import into Route 53. So don't necessarily need to start from scratch here, but once we've got that transformed data set, we then need to look at importing it. And we will use whatever function is available to bulk import that data into the new platform. And then once it's in there, the key step of this bit is to validate that we've got the data in there successfully. A few ways of doing that. So, I use the LDNS tool set. There's a few features in there, a few options to basically do diffs of zones, so compare zones and check that the source data and the target data pretty much match. Or we could do a bunch of queries, do a zone transfer maybe from the original platform, and just do a lookup for each of those records and see that they resolve. Which one's the best? Actually, it's probably not one individual method. It's probably worth doing several of them just to cover all bases and check that you've got no issues there. The likelihood is that stuff will have changed, right? It's maybe quite a dynamic environment. So one of the key steps in this validation piece is to really focus on identifying the key records that might be missing, that might have been skipped for whatever reason during the migration, and be able to focus on those and not burn cycles on dynamic records from DHCP clients that we're not too concerned about. We know they're going to refresh over a period of time. I don't want to be wasting time here trying to work out why Derek's iPhone hostname record doesn't exist in the new platform. And then once we are happy that our data is validated, we can then look at actually cutting the service over. So depending on what we're doing, that might be as much as moving old IP addresses from the old platform to the new one, publishing the new server IPs, NS resource records, or advertising Anycast IPs. But it might be that we can't automatically swing the clients over in one go to point to the new platform, and we still need them to utilize the old DNS service for a while. And so what we might do is we might change our authoritative service to a forwarding service, so clients can still resolve queries via their existing DNS servers, but actually they're just getting the answer from the new data source. I guess one thing here is that the cutover DNS service is it's not necessarily a one-size-fits-all solution. So I remember we did a bunch of AD migrations for a client, and we had a process where we were taking the zones out of AD replication, and that worked really well for half a dozen of the smaller zones. But when we came to do the large production one, we tried that. It was a bit of carnage really for about an hour, just AD replication. We could see zones, they seemed to be going in and out from different servers. Half the zone was missing on some of the servers, and we had about 60 minutes of sweating while we were waiting for AD replication to do its thing. So you also, when you're looking at the cutover, just also consider the size of the environment you're doing and what method really suits the environment for cutting it over. Once we've got the service cut over, we then carry on with the testing phase. So depending on the type of flavor of server it is, check that it answers authoritatively, check I can do DNS updates. If it's recursive, check I can resolve everything I need to resolve. Can I resolve internal stuff, local stuff? Can I resolve internet lookups? A third-party integration's working okay with things like conditional forwarders or stubs. And it's not just you're just checking DNS is working. Get users involved for UAT, check that their applications work, and check platforms that are integrating and consuming DNS can do what they need to do with the new service. And then also continue to monitor it as people and users start to consume the new service. Keep an eye on the logs, check that there's nothing going on. I remember on one migration we had changed an old authoritative service over to a forwarder, and what we found during the validation process is that actually we started seeing a DNS query starting to time out. So looking at the logs, we quickly found that because it was authoritative, but it was now forwarding, it was doing a lot more recursive lookups on behalf of clients, and we started to hit recursive client limits on the service. So bump that value up, and that issue went away.
Mr. Timekeeper, sorry to interrupt, but you have only 2 minutes remaining until the Q&A.
Cool, I am nearly done. So hopefully everything has gone swimmingly well and we are good to go, but sometimes they're just, for whatever, for some unforeseen issues can occur. So we need to work out how we can handle those as part of the migration. And if we know what those issues are, we know what the fix is, we can fix forward, or sometimes we need to understand that, okay, we don't understand what the issue is, the impact is too severe, it's going to take too long to fix, and we're going to need to roll back. And the key thing is, again, as part of that migration plan, is that knowing at each step how we're going to roll back from that and how long it's going to take. And I think really the goal from the migration is essentially to people to be unaware that we've made any change. You know, DNS is like a utility service. No one really complains about it or cares about it too much until it stops flowing. And essentially, as part of the migration, we want to keep that tap flowing and no one to get worried about not being able to surf YouTube for cat videos. So wrap this up, there are definitely benefits to migrating your DNS service, whether you're trying to improve resiliency, consolidate a bunch of environments, bring in new functionality to DNS, and it can be achieved if you put enough planning into it, create that migration plan, test it out so you know pretty much exactly as much as you can do about how the process is going to work and what you're going to do, and validate it as you go through it. Don't just assume that changes have happened. Actually check it out and give yourself the best possible chance of getting it done. That is it. Thank you.
All right, thank you, Kier. Again, you can ask questions by either posting a question in the Q&A tab or by raising your hand. And you're also going to get a poll with a pop-up with a poll that is going to come shortly, so you can rate the talk. We have a couple of questions in the Q&A tab, so I'm going to read through them. The first one is not really a question. It's Andreas Taute that says, thanks, Kier. Just a side note, to get the best result from LDNS compare zones, it helps to canonicalize the zone file with named checkzone -d-o, and Microsoft DNS data needs some cleanup of the DNS timestamp, and then I'm going to spare you spinning out the square brackets and everything. You can find it out in the Q&A page. Then there's a question, or maybe more of a statement from Roland Dobbins. Additional important aspect of DNS migration are zone sanitization, for instance, TsuNAME, and QPS capacity estimation, additional provisioning as necessary.
Yes.
And I think, yeah, go ahead.
Agree. No, I agree with those. And so I did have that in the original talk, and then I realized that I had 5 minutes less than what I actually thought, so I had to slim it down somewhat. But yeah, I mean, Andreas is right, certainly on that. You know, you can, when you're doing the LDNS compare zones, you would typically batch up into a script, so do zone transfers locally, canonicalize them to get them in the right format, and then diff them.
Cool. And I guess maybe one thing that came to mind to me is, do you use tools like such as DNSPerf, for instance, where you can essentially estimate capacity of the new setup, or DNSTAP to be able to actually find out what your clients have been asking, so you can replace that against the new new server and compare results. And I believe DNS-OARC has a bunch of tools that may help also validating new servers. Did you check into those?
Yeah, definitely. So I did have a slide in here which I dropped, which basically said kind of get to know your existing current platform and get to know your target platform. And you're right. I think one thing that a lot of organizations may struggle with is when you ask them what is their current utilization of DNS, what is their, what's their query load. Most people just would not have a clue, and putting a bit of effort into using tools like that. So either, if you can't get that information, you essentially kind of have to overspec the target platform for what you're going to do. But I definitely think there is benefit into putting that time in up front into understanding the actual requirements are in the current existing environment. Any new requirements that may put additional load on, to take those into consideration, and then spec up and implement a new platform accordingly.
All right, I don't see any other questions. We are almost out of time, so I guess I'm going to just hand it over to, well, thanks everybody first, speakers and attendees, and I'm going to hand it over to Keith, who's going to wrap up day one.
Great. Okay, thank you. And also thank you to Huyen for being our timekeeper for the last session. At this point in the day, I think I'd like to thank all of our speakers. They've been absolutely completely on time, so really appreciate that. And I would like to thank our sponsors once more, Farsight and VeriSign, for sponsoring this event. As per my slides, just a quick reminder that in addition to the feedback via the Zoom polls, there's also the chance to give general feedback both on this event and indications of what you think you might want in terms of future events at the survey link there. And then for those of you who still have enough energy or need to imbibe certainties with others in order to continue to have energy, we still have social space. We got a decent number of people in that during the long break. So, if you didn't give spatial chat a go, now is a good chance to do it. That's how you get into there. You'll find the password either an email that we sent you or in the rolling slides, which will come up when I'm done talking. And then we restart tomorrow at 1 a.m. UTC and use the same Zoom link as you did for today. Finally, I would like to thank Maurizio Vergara, who has been doing our social media today, for doing a great sequence of tweets about what's going on in the event. That's us done for today. See you briefly in the shortly in the spatial chat room, and we will resume tomorrow. We'll see you then. Thank you all.